First, Newtonian mechanics of force, a motion, a world that follows predictable rules. An apple falls, a car moves, a planet orbits, and behind it all, one framework explains everything. This is Newtonian mechanics, not quantum, not relativistic, just the classical physics. That shaped our understanding of reality. What is Newtonian mechanics? The paradox asks, if the universe follows strict laws, does that mean everything is predictable? If Newtonian mechanics works on Earth, does that mean it applies everywhere? If motion is just a response to force, does that mean free will is just another form of physics? Different perspectives. Newtonian mechanics works because it provides a framework for motion. Everything that moves follows a rule. Every object in motion stays in motion. Every force has an effect, and suddenly, the universe feels logical. If Newtonian mechanics is so powerful, why did it need to be replaced? What if Newton was not completely right? What if his laws break down? At the quantum level, at the speed of light, would we still trust them? Or would we see that physics needed to evolve? If we reject Newtonian mechanics, do we lose simplicity? What if the universe was more complex? What if Newton's laws were just a good enough model? Would we embrace the uncertainty? Or would we still try to make things predictable? The truth about Newtonian mechanics. The paradox challenges our understanding of determinism versus uncertainty, classical laws versus modern physics. Whether everything follows rules, or if some things will always be unpredictable. If Newtonian mechanics explains motion, does that mean it is the ultimate truth, or just an approximation of reality? 2. Newton's laws of motion. A rule, a formula, a way to predict how everything moves. First law, objects in motion stay in motion. Second law, force equals mass times acceleration. Third law, every action has an equal and opposite reaction. And suddenly, the universe makes sense. Balls roll, cars accelerate, rockets launch, because motion is never random. This is Newton's laws of motion. Not guesses, not theories, just the fundamental truths that govern how everything moves. What are Newton's laws of motion? The paradox asks, if all motion follows these laws, does that mean everything in the universe is predictable? If forces control movement, does that mean there is no true randomness? If every action has an opposite reaction, does that mean nothing ever truly happens in isolation? Different perspectives. Newton's laws work because they create predictability. A ball does not roll without a push. A car does not accelerate without force. An astronaut floats because nothing stops them. And suddenly, motion is not a mystery. It is a set of rules. If Newton's laws are true, why do we need Einstein? What if motion is not always predictable? What if time slows down? What if mass warps space? Would Newton's laws still hold? Or would we see that the universe is deeper than simple rules? If we follow Newton's laws, can we control the universe? What if we mastered every force? What if we predicted every movement? Would we gain complete control? Or would we still find chaos in the system? The truth about Newton's laws of motion. The paradox challenges our understanding of predictability versus randomness, Newton versus Einstein, whether motion is just physics or something deeper. If every action has an equal reaction, does that mean nothing in the universe ever happens without a cause? Third law of universal gravitation. A force, an attraction, a pull that connects everything. An apple falls, a planet orbits, a star collapses, and behind it all, one equation explains it. F equals g m sub 1m sub 2 divided by r squared. The more massive the object, the stronger the pull, the closer the distance, the greater the force. This is the law of universal gravitation. Not just a law, not just a force, but the invisible thread that holds the universe together. What is the law of universal gravitation? The paradox asks, if gravity is universal, Does that mean every object in the universe is affecting every other object? If gravity works at a distance, does that mean space itself is connected? If gravity is always pulling, does that mean the universe will eventually collapse? Different perspectives. The law of universal gravitation works because gravity is always acting. The Earth pulls the moon, the sun pulls the planets, a black hole warps space. Because gravity never stops working. It is always pulling, even when you do not feel it. If gravity is so simple, why do we need general relativity? What if gravity is not a force, but a warping of space-time? What if Newton's law is just an approximation? Would we still trust it, or would we see separate? Fourth, applications of Newtonian mechanics. A movement, a calculation, a law that governs motion and shapes the world around us. A car accelerates, a rocket launches, a pendulum swings. Every action follows a precise equation. Every force produces a predictable effect. From engineering to astronomy, from bridges to satellites, Newtonian mechanics builds civilization. This is applications of Newtonian mechanics. Not just equations, not just theory, but the foundation of everything that moves. What are the applications of Newtonian mechanics? The paradox asks, if Newton's laws describe motion, does that mean we can predict everything? If every force has an effect, does that mean free will is just another reaction? If Newtonian mechanics explains machines and planets, does that mean the universe is just a giant system of gears? Different perspectives. Newtonian mechanics works because it provides precision in the physical world. Every machine, every structure, every moving object follows these same rules, and that is why science trusts Newton. If Newtonian mechanics is so powerful, why do we need quantum mechanics? What if objects do not just move, but also behave like waves? What if small particles do not follow Newton's laws at all? Would we still believe that physics is predictable? If we master Newtonian mechanics, can we control everything? What if we knew every force? What if we could predict every motion? Would we control reality? Or would we still find uncertainty in the details? The truth about applications of Newtonian mechanics. The paradox challenges our understanding of prediction versus randomness, Newton versus modern physics, whether motion is just physics or something deeper. If Newtonian mechanics explains motion, does that mean everything is just a series of predictable reactions? 5. Limitations of Newtonian mechanics. A theory, a framework, a set of rules that seemed unbreakable until they broke. Newton's laws explain motion, they explain forces, they explain almost everything, except when they don't. Light does not follow them. Time does not follow them. Gravity does not act the way Newton expected. And suddenly, Newton is not enough. This is the limitations of Newtonian mechanics. Not the end of physics, not the end of motion. Just a sign. That reality is more complex than we thought. What are the limitations of Newtonian mechanics? The paradox asks, if Newtonian mechanics does not work at all scales, does that mean it was never complete? If motion changes at high speeds, does that mean Newton's laws were just an approximation? If space-time is curved, does that mean forces do not actually exist as Newton described? Different perspectives. Newtonian mechanics fails at the speed of light. A train accelerates, a rocket moves faster, and suddenly, time slows down, mass increases, and Newton's laws stop working. If Newton was wrong, does that mean everything we knew about physics is wrong? What if forces do not exist? What if gravity is not a pull, but a warping of space? Would Newton still be useful? Or would we need a new way to see reality? If Newton's laws are limited, should we stop teaching them? What if Newton's laws were just a good enough model? What if they work most of the time, but fail at extremes? Would we still use them? Or would we finally move on to something better? the truth about the limitations of Newtonian mechanics. The paradox challenges our understanding of classical versus modern physics, prediction versus uncertainty, whether physics is complete or just evolving. If Newton's laws fail at the quantum and cosmic scale, does that mean we are still missing the full picture? 6. Thermodynamics basics. A system, a temperature, a law that governs energy itself. Heat flows, engines run, stars burn, and behind it all, thermodynamics sets the rules. Energy cannot be created or destroyed. Heat always moves from hot to cold. Disorder always increases. This is thermodynamics basics, not just about heat, not just about work, but about why the universe changes and why it will never be the same again. What are the basics of thermodynamics? The paradox asks, if energy cannot be destroyed, does that mean nothing ever truly disappears? If heat always moves toward equilibrium, does that mean the universe is running out of usable energy? If entropy always increases, does that mean time only moves in one direction? Different perspectives. Thermodynamics works because it explains energy at every level, from steam engines to black holes, from living cells to the entire universe. Energy follows the same rules. If entropy always increases, does that mean the universe will end in chaos? What if energy is spreading out? What if everything is cooling down? Would the universe eventually stop functioning? Or would we still find order in the chaos? If we Seventh, zeroth law of thermodynamics. A system, a balance, a rule so simple that it was discovered last. Two objects are in thermal equilibrium. A third object is in thermal equilibrium with one of them, then all three must be in thermal equilibrium with each other. It seems obvious. It seems basic, but without it, the rest of thermodynamics falls apart. This is the zeroth law of thermodynamics. Not about heat transfer, not about energy loss, just a law that defines what it means for temperatures to be equal. What is the zeroth law of thermodynamics? The paradox asks, if temperature is just a measurement, does that mean thermal equilibrium is only a human concept? If two objects are in equilibrium separately, does that mean they are always in equilibrium together? If heat transfer always happens until balance is reached, does that mean the universe is always seeking stability? Different perspectives. The zeroth law works because it defines temperature scientifically without it. We could not measure heat. We could not build thermometers. We could not understand equilibrium, because balance is the foundation of thermodynamics. If everything seeks thermal equilibrium, does that mean the universe is trying to cool down? What if every object in the universe is slowly reaching balance? What if all energy differences are disappearing? Would that mean the universe is heading toward absolute stillness? If we control thermal equilibrium, do we control energy flow? What if we stopped heat from spreading? What if we engineered perfect balance? Would we gain infinite energy? Or would we still be trapped by the laws of physics? The truth about the zeroth law of thermodynamics. The paradox challenges our understanding of temperature versus equilibrium, balance versus energy transfer, whether the universe is always seeking equilibrium, or if some things will always remain unbalanced. If thermal equilibrium is always reached, does that mean the universe is heading toward a state of absolute uniformity? 8. First law of thermodynamics, energy conservation. An engine, a reaction, a rule that says nothing is ever lost. Energy cannot be created. Energy cannot be destroyed. It can only be transformed, from heat to work, from motion to electricity, from the sun to life. This is the first law of thermodynamics. Not just a rule, not just an equation, but a statement that energy will always exist. What is the first law of thermodynamics? The paradox asks, if energy can never be created or destroyed, does that mean the total energy of the universe is constant? If energy only changes form, does that mean destruction is just another kind of transformation? If we cannot create energy, does that mean we are only borrowing it from other sources? Different perspectives. The first law works because it connects every energy system. A battery charges, a fire burns, a planet orbits, and in every case, energy is never lost. It just changes form. If energy is never destroyed, where did it come from? What if energy was always here? What if it never had a beginning? Would that mean the universe never truly started? If we could control energy perfectly, could we create perpetual motion? What if we recycled energy perfectly? What if we stopped losing energy to waste? Would we achieve infinite motion, or would we still be bound by the limits of reality? Ninth, second law of thermodynamics, entropy. A system, a process, a rule that says everything moves toward disorder. Hot things cool down, ice melts, stars burn out, and every action increases entropy. The universe is winding down. Energy is spreading everywhere, and one day, everything will be uniform and still. This is the second law of thermodynamics. Not about energy, not about motion, just a truth. That time moves forward because disorder always increases. What is the second law of thermodynamics? The paradox asks, if entropy always increases, does that mean the universe will eventually reach maximum disorder? If energy spreads out over time, does that mean the universe is slowly running out of useful energy? If entropy never decreases, does that mean time only moves in one direction? Different perspectives. The second law explains why time only moves forward. A glass shatters, a star collapses, a fire burns out, and yet you never see them reverse, because entropy always increases. If entropy increases, does that mean the universe will end in heat death? What if one day all energy is evenly spread out? What if there are no temperature differences left? Would that mean the universe reaches a final motionless state? If we could reverse entropy, could we reverse time? What if we could force order to return? What if we could stop the spread of energy? Would we control time itself? Or would we still be pulled forward by the arrow of entropy? 10th, third law of thermodynamics, absolute zero. A limit, a boundary, a temperature so low that motion itself stops. As heat is removed, molecules slow, atoms freeze in place until at absolute zero. There is no movement left, no vibration, no energy, just perfect stillness. But can we ever reach it? This is the third law of thermodynamics, not just about cold, not just about heat loss, but a fundamental limit on how cold anything can get. What is the third law of thermodynamics? The paradox asks, if absolute zero is the lowest possible temperature, does that mean we can never fully reach it? If motion stops at absolute zero, does that mean energy itself disappears? If nothing can be colder than absolute zero, does that mean there is a limit to how much disorder we can remove? Different perspectives. The third law works because temperature is a measure of motion. The hotter something is, the faster its atoms move. The colder it gets, the slower they become. But at absolute zero, all movement stops. If we could reach absolute zero, would we break physics? What if all motion ceased? What if entropy stopped increasing? Would that mean time itself froze? If absolute zero is unreachable, does that mean there is always some heat left? What if we got close? What if we reached 99.999% of absolute zero? Would there still be some tiny motion? Or would we finally achieve the impossible? The truth about the third law of thermodynamics. The paradox challenges our understanding of temperature versus motion limits versus reality. Whether we can ever truly stop all movement, or if there will always be energy left. If absolute zero can never be reached, does that mean motion never fully stops? 11th applications of thermodynamics. A system, a reaction, a process where heat and energy shape everything. Engines convert fuel into motion. Refrigerators move heat away. Stars burn hydrogen to keep galaxies alive. Everything that does work follows the laws of thermodynamics. This is applications of thermodynamics, not just about heat, not just about entropy, but about how energy flows and why nothing happens without it. What are the applications of thermodynamics? The paradox asks, if thermodynamics controls energy, does that mean it controls all physical processes? If engines, stars, and life itself depend on thermodynamics, does that mean everything is just energy transfer? If energy is always moving, does that mean everything is just a system waiting to lose heat? Different perspectives. Thermodynamics works because energy must flow. A car moves, a storm forms, a battery charges, and in each case, energy is transferred, lost, and transformed. If we master thermodynamics, can we create infinite energy? What if we harnessed all waste heat? What if we found a perfect cycle? Would we create a machine that never stops? Or would we still be bound by entropy? If thermodynamics explains everything, is life just another energy process? What if we are just systems? What if thoughts, emotions, and decisions are just energy moving through neurons? Would that mean life is just another physical reaction? Or would we still believe in something bigger? 12th, thermodynamics in astrophysics, a star, a galaxy, a universe driven by heat, motion, and energy. Stars burn because of fusion. Planets form because of gravity and heat. Black holes exist because of thermodynamic collapse. Every explosion, every orbit, every cosmic event follows the laws of thermodynamics. This is thermodynamics in astrophysics, not just about space, not just about stars, but about how energy moves across the universe and how that determines everything we see. What is thermodynamics in astrophysics? The paradox asks, if thermodynamics governs space, does that mean the fate of the universe is already determined? If entropy always increases, does that mean stars will all burn out one day? If black holes absorb energy, does that mean they are thermodynamic engines of destruction? Different perspectives. Thermodynamics shapes everything from stars to black holes. The sun burns, supernovas explode, galaxies collide, and behind all of it, energy is being transformed. If the universe follows thermodynamics, is heat death inevitable? What if all temperature differences disappeared? What if all energy was evenly spread? Would that mean the universe reaches its final motionless state? If we could reverse entropy, could we prevent the death of the universe? What if we could stop heat from spreading? What if we could recycle lost energy? Would we keep the universe alive? Or would we still be doomed to the cold darkness of the future? 13. Electromagnetism. Basics. A force, a charge, a hidden power that shapes the universe. A magnet pulls, a spark jumps, a current flows, and behind it all, electricity and magnetism are the same force. They move together. They influence each other. They create light itself. This is electromagnetism basics, not just wires, not just fields, but the fundamental force that powers the modern world. What are the basics of electromagnetism? The paradox asks, if electricity and magnetism are linked, does that mean they are just two sides of the same reality? If electromagnetism governs everything from circuits to stars, does that mean it is the most fundamental force? If light is an electromagnetic wave, does that mean we are surrounded by invisible energy fields at all times? Different perspectives. Electromagnetism works because it unifies. Two seemingly different forces. A magnet moves electrons. A changing electric field creates magnetism. One does not exist without the other, and suddenly, the universe feels connected. If electromagnetism is everywhere, can we ever escape it? What if every atom is charged? What if every force we feel is electromagnetic? Would that mean everything is just interacting fields? If we master electromagnetism, can we control the world? What if we harnessed every field? What if we controlled charge perfectly? Would we create unlimited energy, or would we still be bound by its fundamental limits? The truth about electromagnetism. Basics. The paradox challenges our understanding of electricity versus magnetism, forces versus reality, whether everything we see is just a result of electromagnetic interactions. If electromagnetism rules the universe, does that mean everything is just moving charges and invisible fields? 14. Electric fields and charge interactions. A push, a pull, a force that acts at a distance. A proton attracts an electron. Two like charges repel each other. No contact, no physical touch, just invisible forces stretching across space. This is electric fields and charge interactions. Not just static, not just attraction, but the reason every atom in the universe holds together. What are electric fields and charge interactions? The paradox asks, if electric fields act at a distance, does that mean they extend forever? If opposite charges attract, does that mean every particle is being pulled toward something else? If electrons orbit due to charge forces, does that mean electromagnetism is the reason atoms exist? Different perspectives. Electric fields work because charges shape the space around them. A positive charge creates a field. A negative charge feels its pull. And suddenly, forces exist without contact. If electric fields extend forever, are we always feeling their effects? What if every particle in the universe affects every other particle? What if electric fields never truly fade? Would that mean every charge is connected to everything else? If we manipulate electric fields, can we create wireless energy? What if we moved charge without wires? What if we beamed electricity through air? Would we create a world of infinite power? Or would we still be limited by physics itself? 15. Magnetic fields and moving charges. A loop, a motion, a force that emerges from movement. A charge sits still. No magnetism. A charge moves. A magnetic field appears. A current flows. A magnet forms. Electricity and magnetism are not separate. They are connected by motion. This is magnetic fields and moving charges, not just attraction, not just polarity, but the reason why electromagnetism is one of nature's fundamental forces. What are magnetic fields and moving charges? The paradox asks, if magnetism only exists when charges move, does that mean a static charge has no magnetic effect? If electricity and magnetism are linked, does that mean they are just different views of the same force? If motion creates magnetism, does that mean the entire universe is filled with unseen magnetic interactions? Different perspectives. Magnetism works because motion creates fields. A current moves. A magnetic force appears. And suddenly, every wire is a potential magnet. If magnetic fields are everywhere, are we always affected by them? What if every moving charge affects us? What if every circuit, every wire, every device creates a field that touches everything else? Would that mean we live inside a world shaped by invisible forces? If we master magnetic fields, do we unlock new technology? What if we controlled magnetic forces? What if we moved objects without touching them? Would we create hovering machines, wireless power, and advanced propulsion? Or would we still be learning the deeper mysteries of electromagnetism? 16th electromagnetic induction. A coil, a motion, a force that creates electricity from movement. Move a magnet past a wire, and suddenly, a current appears. Spin a coil inside a magnetic field, and suddenly, power is generated. This is electromagnetic induction, not just a discovery, not just a theory, but the principle that powers the modern world. What is electromagnetic induction? The paradox asks, if moving a magnet creates electricity, Does that mean energy is hidden in motion itself? If changing a magnetic field creates a current, does that mean magnetism can be used as an infinite power source? If electricity and magnetism generate each other, does that mean they are just different forms of the same force? Different perspectives. Electromagnetic induction works because motion creates energy flow. A wind turbine spins. A hydroelectric dam moves water past coils. A car alternator recharges the battery while driving. And suddenly, mechanical motion becomes electricity. If we master induction, do we unlock wireless power? What if we transferred energy without wires? What if we created power fields that charge devices remotely? Would that mean a future without batteries? If induction can create energy, can it also take it away? What if a field stopped currents? What if a signal blocked power flow? Would we create silent weapons? Or would we still be learning the true potential of electromagnetism? The truth about electromagnetic induction. The paradox challenges our understanding of motion versus energy, wires versus wireless power. Whether electricity and magnetism are just two perspectives of the same reality. If moving a magnet creates energy, does that mean motion itself is just hidden electricity waiting to be used? 17th, Maxwell's equations and unification of electromagnetism. A formula, a unification, a set of 4 equations that explain everything about electricity and magnetism. Electric fields change, magnetic fields move, charges create forces, currents generate fields, and suddenly, the universe makes sense. This is Maxwell's equations and the unification of electromagnetism. Not just a breakthrough, not just another law, but a discovery that showed light itself is an electromagnetic wave. What are Maxwell's equations? The paradox asks, if 4 equations describe all of electromagnetism, does that mean everything about the force is predictable? If light is an electromagnetic wave, does that mean we are constantly surrounded by unseen energy? If Maxwell unified electricity and magnetism, does that mean all forces are waiting to be unified? Different perspectives. Maxwell's equations work because they describe how fields interact. A charge moves, a field changes, a wave forms, and suddenly, everything from power lines to radio waves follows the same math. If light is an electromagnetic wave, does that mean the universe is made of energy? What if everything is just vibrations of fields? What if matter is just trapped energy? Would that mean physics is really just the study of waves? If electromagnetism was unified, can we do the same for other forces? What if we found the link between electromagnetism and gravity? What if we connected quantum mechanics with classical physics? Would we finally understand everything? Or would we still find deeper mysteries waiting to be solved? 18. The electromagnetic spectrum. A frequency, a wavelength, a spectrum of invisible forces that surround us. Radio waves carry voices, microwaves heat food, infrared sees through darkness. Visible light lets us see. Ultraviolet burns our skin. X-rays look through bodies. Gamma rays tear atoms apart, but they are all the same thing. This is the electromagnetic spectrum, not different forces, not separate effects, just one continuous field. That spans from long waves to deadly radiation. What is the electromagnetic spectrum? The paradox asks, if radio waves and gamma rays are both electromagnetic waves, does that mean light is just another kind of radiation? If the visible spectrum is tiny, does that mean most of reality is invisible to us? If all waves follow the same rules, does that mean we can harness any part of the spectrum? Different perspectives. The electromagnetic spectrum works because waves are everywhere. A phone call, a Wi-Fi signal, a light beam, all of them are just waves moving through space. If we can manipulate the spectrum, do we control information? What if we tuned into more frequencies? What if we used higher energy waves? Would we create new forms of communication? Or would we risk damaging reality itself? If most of the spectrum is invisible, what else are we missing? What if we could see radio waves? What if we felt gamma rays? Would reality look different? Or are we already trapped in a tiny window of perception? 19th, special relativity basics. A speed, a limit, a reality that defies common sense. You move fast. Time slows down, space contracts, mass increases. At the speed of light, physics transforms. This is special relativity, not just a theory, not just an equation, but a new way of seeing the universe. What are the basics of special relativity? The paradox asks, if time and space change at high speeds, does that mean reality is relative? If the laws of physics stay the same for all observers, does that mean motion is just a perspective? If nothing can go faster than light, does that mean the speed of light is the ultimate cosmic limit? Different perspectives. Special relativity works because it redefines motion. A moving observer sees the world differently. A stationary observer sees time as constant, but both are correct. Because in relativity, there is no absolute frame of reference. If time and space are not fixed, what is real? What if your clock ticks slower than mine? What if your ruler shrinks while you move? Would that mean reality depends on how you move? If we could reach the speed of light, would we escape time itself? What if we moved fast enough? What if we bent time and space? Would we see the past and future at once? Or would we still be bound by the fundamental limits of the universe? The truth about special relativity. The paradox challenges our understanding of motion versus perspective, speed versus time, whether reality is fixed or just relative to how we move. If time and space change depending on speed, does that mean there is no single true reality? 20. Time dilation. A clock, a journey, a slower passage of time. That defies expectation. Move closer to the speed of light, and your watch ticks slower. Travel near a black hole, and time nearly stops. For you, everything feels normal. For others, centuries may pass. This is time dilation, not a theory, not an illusion, but a measurable effect. That shows time is not absolute. What is time dilation? The paradox asks. If time slows at high speeds, does that mean astronauts experience less aging? If time is affected by motion and gravity, does that mean time is just another dimension? If time can be stretched, does that mean it could ever be reversed? Different perspectives. Time dilation works because motion and gravity warp space-time. A fast-moving object ages slower. A strong gravitational field bends time. And suddenly, the flow of time is no longer constant. If time can slow, could it stop completely? What if we moved at the speed of light? What if we entered a black hole's event horizon? Would time freeze forever? Or would we experience something beyond human understanding? If we master time dilation, can we control time itself? What if we traveled close to light speed? What if we extended our lifespan by moving faster? Would we reach the far future without ever aging? Or would we still be limited by the laws of physics? The truth about time dilation. The paradox challenges our understanding of time versus motion, aging versus speed, whether time is an absolute reality or just another flexible dimension. If time slows down at high speeds, does that mean we are all experiencing different versions of time? 21st, length contraction. A ruler, a measurement, a shrinking of space. That depends on how fast you move. You fly past at near light speed, and I see your spaceship shrink. You measure it inside. And for you, nothing changes. Because in relativity, motion changes the way we see space. This is length contraction, not a trick, not an illusion, but a real effect. That means space itself shrinks when you move fast enough. What is length contraction? The paradox asks, if space contracts at high speeds, does that mean objects physically shrink? If two observers measure different lengths, does that mean distance is just a perspective? If the universe looks different depending on motion, does that mean space is not an absolute reality? Different perspectives. Length contraction works because space and time are connected. A moving object experiences time differently. A moving object experiences space differently. And suddenly, the world shrinks as speed increases. If space can contract, could it vanish completely? What if we moved at the speed of light? What if our length contracted to zero? Would that mean we existed everywhere at once? If we control length contraction, can we shorten distances in space travel? What if we traveled close to light speed? What if the journey that took years now took seconds because distance itself contracted? Would that mean instant travel? Or would we still face the limits of relativity? 22. The relativity of simultaneity. A moment, an event, a reality where now is not the same for everyone. A flash of lightning strikes at both ends of a moving train. An observer on the train sees them happen at different times. An observer on the ground sees them happen together. Who is correct? Both of them. Because in relativity, time is not absolute. This is the relativity of simultaneity, not just a strange idea, not just a theory, but a fundamental truth. That shows time depends on where and how you observe it. What is the relativity of simultaneity? The paradox asks, if two people see the same event happen at different times, does that mean there is no universal now? If simultaneity depends on motion, does that mean the past, present, and future are relative? If time flows differently for different observers, does that mean cause and effect are subjective? Different perspectives. The relativity of simultaneity works because motion affects time perception. A person on a train sees one order. A person on the ground sees another. Both are correct because there is no single universal timeline. If simultaneity is relative, does that mean time travel is possible? What if we could manipulate motion? What if we controlled speed? Would that mean we could change the order of events? Or would we still be trapped by the deeper rules of reality? If every observer has their own now, what is the true present? What if we are all experiencing different slices of time? What if the present does not exist as a fixed moment? Would that mean time is just an illusion we agree on? 23rd, E equals mc squared and mass energy equivalence A formula, a revelation, a simple equation. That changed the universe. Energy is not separate from matter. Matter is just energy in another form. A tiny bit of mass can release an enormous amount of energy. And suddenly, the universe is not just made of particles. It is made of energy itself. This is E equals mc squared and mass energy equivalence. Not just a theory, not just a number, but a fundamental law that powers stars, fuels nuclear bombs, and shapes reality itself. What is E equals mc squared and mass energy equivalence? The paradox asks, if mass and energy are the same, does that mean everything is just energy in a different form? If a small mass can release huge energy, does that mean energy is just compressed mass? If matter is energy, does that mean the universe is a vast sea of hidden energy waiting to be unlocked? Different perspectives, E equals mc squared works, because it connects the physical and the energetic. A nuclear reaction releases energy. A particle collides and transforms into light. A star burns fuel by turning mass into pure radiation. And suddenly, matter is just a temporary form of energy. If energy and mass are equivalent, could we convert one into the other at will? What if we turned energy into matter? What if we transformed mass into pure power? Would that mean we could create something from nothing? If everything is energy, is reality just a form of light? What if solid objects were just concentrated energy fields? What if all that exists is vibration and waves? Would that mean matter is an illusion? Or would we still see the universe as something tangible? 24. Real-life applications of special relativity. A satellite, a GPS signal. A world that relies on relativity every day, GPS must adjust for time dilation. Particle accelerators must account for relativistic mass. Nuclear energy is only possible because of mass-energy equivalence. And every time we measure light, we are seeing the speed limit of the universe in action. This is real-life applications of special relativity, not just space travel, not just black holes, but a technology-driven reality. That depends on Einstein's equations. What are the real-life applications of special relativity? The paradox asks, if relativity affects everyday technology, does that mean we live in a relativistic world without realizing it? If GPS needs relativity to function, does that mean time is already moving differently at different altitudes? If mass-energy equivalence powers nuclear reactions, does that mean the energy of the universe is hidden in plain sight? Different perspectives. Special relativity works because it affects everything, moving at high speeds. A satellite in orbit ticks faster. A particle in an accelerator gains mass. A nuclear reaction transforms mass into energy. And suddenly, relativity is not just theory, it is technology. If relativity shapes technology, can we use it for future space travel? What if we moved near light speed? What if we used relativistic effects to extend lifetimes? Would that mean interstellar travel is possible? If we ignore relativity, would modern technology stop working? What if we never corrected for time dilation? What if we ignored relativistic mass in physics experiments? 25th, general relativity basics, a mass, a curve, a force that is not really a force, but the bending of space itself. Newton saw gravity as a pull. Einstein saw gravity as a curve. A massive object sits in space, and space bends around it. Planets do not orbit because they are pulled. They orbit because they follow the curves of space-time. This is general relativity, not just a new equation, not just a better model, but a completely different way to see reality itself. What is general relativity? The paradox asks, if gravity is not a force, does that mean falling is just moving through curved space-time? If space can bend, does that mean time can bend too? If gravity is just geometry, does that mean we live inside a four-dimensional landscape we can never see? Different perspectives. General relativity works because it explains gravity at every scale. An apple falls, a planet orbits, a black hole distorts time itself, and in every case, gravity is just the warping of space. If space and time are linked, does that mean time is just another dimension? What if time is flexible? What if the past, present, and future coexist? Would that mean we are all just travelers in a four-dimensional landscape? If we control gravity, can we control reality? What if we could bend space-time at will? What if we could reshape gravity itself? Would we create warp drives, time loops, and artificial black holes? Or would we still be bound by the deeper rules of the cosmos? The truth about general relativity. The paradox challenges our understanding of gravity versus space-time forces versus geometry. Whether the universe is just a four-dimensional shape waiting to be explored, if gravity is not a force, does that mean we are all just falling through the curves of space itself? 26. Gravity as the warping of space-time. A distortion, a ripple, a bending of reality itself. A planet moves because space is curved. A star collapses, and space bends infinitely. A black hole forms, and time itself slows down, because mass tells space how to curve, and space tells objects how to move. This is gravity as the warping of space-time, not Newton's force, not an invisible pull, but the fabric of reality shaping itself. What is gravity as the warping of space-time? The paradox asks, if space-time is curved, does that mean straight lines do not exist? If gravity is just geometry, does that mean there is no such thing as weight? If time slows near strong gravity, does that mean the past and future can stretch? Different perspectives. Gravity works because it bends space itself. A planet follows a curve. A light beam bends near a star. A clock slows down in deep gravity. Because mass changes the shape of reality. If space can warp, can we ever travel faster than light? What if we bent space instead of moving through it? What if we curled space-time around us? Would we reach distant galaxies instantly, or would we still be trapped by the limits of physics? If space is a fabric, can it tear? What if a black hole ripped space apart? What if the universe was stretched too far? Would we see holes in reality itself? Or would space always find a way to rearrange itself? 27th gravitational time. Dilation, a clock, a depth, a slowing of time itself, caused by gravity. You stand on Earth. Time ticks normally. You move near a black hole. Time slows to a crawl. For you, seconds pass. For the universe, centuries fly by. Because gravity does not just bend space, it bends time itself. This is gravitational time dilation. Not an illusion, not a theory, but a measurable effect. That proves time is not absolute. What is gravitational time dilation? The paradox asks, if gravity slows time, does that mean time flows differently in different places? If time is relative, does that mean there is no single universal now? If strong gravity slows time to almost nothing, does that mean black holes could be natural time machines? Different perspectives. Gravitational time dilation works because gravity bends space and time together. A clock on a mountain ticks faster. A clock near a black hole nearly stops because gravity and time are linked. If time can slow, could it ever reverse? What if gravity became infinitely strong? What if time stopped completely? Would that mean reversing time is possible? If we control gravity, do we control time? What if we could manipulate space-time curvature? What if we built artificial gravity wells? Would we create time bubbles, time warps, and time loops? Or would we still be trapped by the relentless arrow of time? 28th. Gravitational waves. A ripple, a tremor, a disturbance in space-time itself. Two black holes collide, and space shakes. A neutron star collapses, and time trembles. Not sound, not light, but waves, moving through the very fabric of reality. This is gravitational waves, not a theory, not just an idea, but a measured effect. That proves space itself is not static. What are gravitational waves? The paradox asks, if space can ripple, does that mean it behaves like a fluid? If gravitational waves move at the speed of light, does that mean they carry information across the universe? If massive collisions send waves through reality, does that mean we are always feeling the echoes of the past? Different perspectives. Gravitational waves work. Because space-time is flexible, a star explodes, a black hole spins, a galaxy merges, and the universe feels it. Because space is not rigid, it shakes like a fabric. If gravitational waves travel across the cosmos, can we use them to see the past? What if we listened to these waves? What if we heard the echoes of the Big Bang? Would we uncover the history of the universe itself? If we could control gravitational waves, could we send messages across the stars? What if we generated our own ripples? What if we sent gravitational pulses? Would we create a new kind of communication? Or would space-time itself resist being manipulated? The truth about gravitational waves. The paradox challenges our understanding of space versus motion, ripples versus forces. Whether the universe is static or constantly vibrating. If space can shake, does that mean reality is never truly still? 29th. Black holes and general relativity. A collapse, a void, a place where space and time break down. A star dies, and gravity pulls in everything. Light cannot escape. Time slows to a crawl. At the center, a singularity forms, a place where the laws of physics fail. This is black holes and general relativity, not a hole, not a void, but the ultimate consequence of bending space-time too far. What are black holes and general relativity? The paradox asks, if gravity can collapse space, does that mean there is a limit to how much mass reality can hold? If nothing can escape a black hole, does that mean information is lost forever? If time stops at the event horizon, does that mean entering a black hole is falling into eternity? Different perspectives. Black holes exist because gravity has no limit. A massive object bends space. A heavier object bends it more. A black hole tears space apart. Because gravity does not stop, it only gets stronger. If black holes trap everything, does that mean information can disappear? What if data falls in? What if nothing comes out? Would that mean the universe can forget? Or would information always find a way to escape? If we could enter a black hole, what would we see? What if we crossed the event horizon? What if time stopped for us, but the universe moved on? Would we see the end of time? Or would we still be trapped in a cosmic paradox? 30. Practical applications of general relativity. A signal, a clock, a world that relies on relativity every day. GPS satellites adjust for gravitational time dilation. Particle accelerators correct for relativistic mass increase. Astronomers use relativity to predict the motion of planets. And without these adjustments, modern technology would fail. This is practical applications of general relativity, not just space travel, not just black holes, but a science that shapes our everyday lives. What are the practical applications of general relativity? The paradox asks, if relativity affects everyday technology, does that mean we live in a relativistic world without realizing it? If GPS requires time dilation corrections, does that mean we already experience different versions of time? If relativity can predict gravitational lensing, does that mean we can use it to see distant parts of the universe? Different perspectives. General relativity works because it affects everything that moves. A satellite orbits. Time slows down. A high-speed train travels. Time shifts. A gravitational field warps space. Light bends. And suddenly, relativity is not just theory, it is technology. If we can use relativity to correct clocks, can we use it to extend life? What if we moved at near light speed? What if we lived in strong gravity? Would we age slower than the rest of the world? Would that mean relativity could alter human lifespans? If relativity affects technology, what else could it improve? What if we designed energy systems that used relativistic effects? What if we harnessed space-time itself for computing? Would that mean relativity could push the limits of engineering, or would we still be scratching the surface of Einstein's discoveries? 31st. Quantum mechanics basics. A particle, a wave, a reality where certainty disappears. An electron moves, but we cannot know its exact position. A photon exists, but it is both a wave and a particle. A measurement is made, and the universe chooses an outcome. This is quantum mechanics, not just small physics, not just uncertainty, but a fundamental rewrite of what we thought reality was. What are the basics of quantum mechanics? The paradox asks, if we can never know both position and momentum exactly, does that mean the universe is inherently uncertain? If quantum particles exist in many states until observed, does that mean reality is shaped by observation? If quantum effects control the microscopic world, does that mean they also influence our daily lives? Different perspectives. Quantum mechanics works because probability defines reality. An electron does not have a single location. A photon does not have a fixed path. Everything exists in a cloud of probabilities until it is measured. Then, and only then, reality collapses. If quantum mechanics is real, does that mean the universe is random? What if there is no deeper law? What if particles just choose their outcomes randomly? Would that mean reality is governed by chance? Or is there still something hidden beneath? If we master quantum mechanics, can we control reality? What if we harnessed quantum states? What if we used superposition, entanglement, and tunneling? Would we unlock new forms of technology, or would we still be bound by the mysteries of the quantum world. 32. The wave-particle duality. A paradox, a contradiction, a particle that is also a wave. Light moves in waves until we measure it. Electrons spread like waves until we detect them. And suddenly, the universe is not made of solid objects. It is made of wave-like probabilities. This is the wave-particle duality, not just an observation, not just an experiment, but a fundamental mystery of how things behave on the smallest scales. What is the wave-particle duality? The paradox asks, if something acts like a wave and a particle, does that mean it is both at once? If measurement forces something to act like a particle, does that mean observation changes reality? If matter behaves like waves, does that mean solid objects are just concentrated waveforms? Different perspectives. The wave-particle duality works because nature does not follow classical logic. A photon interferes with itself like a wave, but it lands on a detector like a particle. An electron spreads out, but hits a target as a single point. Because in the quantum world, things do not have fixed identities. If everything is a wave, does that mean solid objects are an illusion? What if atoms were just standing waves? What if particles were just disturbances in fields? Would that mean matter is just an emergent property of energy? If we control wave-particle duality, can we create new forms of matter? What if we manipulated quantum waves? What if we controlled when something acts like a wave or a particle? Would we create new physics, new technology, new realities? Or would we still be limited by the laws of quantum mechanics? 33. The double-slit experiment. A screen, a barrier, a beam of light. That should behave like particles, but instead acts like a wave. Photons pass through two slits and create an interference pattern, as if they traveled through both slits at once. But when we measure them, the pattern disappears. This is the double-slit experiment, not just a test, not just an anomaly, but the most famous demonstration. That observation changes reality. What is the double-slit experiment? The paradox asks, if a particle interferes with itself, does that mean it takes multiple paths at once? If measuring a particle collapses the wave, does that mean consciousness affects physics? If quantum objects exist in probabilities, does that mean the universe only becomes real when it is observed? Different perspectives. The double-slit experiment works because reality exists as probability until measured. A photon acts like a wave. Until we check where it lands, an electron interferes with itself, until we watch its path, and suddenly, observation itself becomes part of physics. If measurement affects reality, does that mean consciousness shapes the universe? What if the universe only exists when observed? What if reality is just potential until someone looks at it? Would that mean our minds are part of the equation? If we understand the double-slit experiment, do we unlock quantum control? What if we harnessed wave-like behavior? What if we forced quantum superpositions to work for us? Would we create instant teleportation, perfect encryption, unlimited computing power? Or would we still be discovering the deeper secrets of reality? 34. Heisenberg's uncertainty principle. A measurement, a limit, a rule that says you cannot know everything at once. You measure a particle's position, and its momentum becomes uncertain. You measure its momentum, and its position becomes blurry. No matter how precise you try to be, nature refuses to let you see both. This is Heisenberg's uncertainty principle, not just a limitation, not just bad measurement, but a fundamental truth. That says reality itself is built on uncertainty. What is Heisenberg's uncertainty principle? The paradox asks, if measuring one property makes another uncertain, does that mean reality is always in flux? If precision has limits, does that mean knowledge is always incomplete? If uncertainty is built into physics, does that mean the universe is unpredictable at its core? Different perspectives. The uncertainty principle works because particles exist as waves. A particle moves, a wave spreads, and suddenly, its exact position is impossible to pin down. If we can never know everything, does that mean the future is undetermined? What if we cannot predict motion perfectly? What if particles follow probabilities instead of strict paths? Would that mean reality itself is built on randomness? If we control uncertainty, do we control the quantum world? What if we engineered perfect measurement techniques? What if we reduced uncertainty to near zero? Would we unlock new physics? Or would we still be bound by the fundamental limits of nature? The truth about Heisenberg's uncertainty principle. The paradox challenges our understanding of knowledge versus limitation, waves versus particles, whether reality is truly predictable or forever uncertain. If uncertainty is a fundamental rule, does that mean reality is always partly unknown? 35th, quantum superposition, a state, a possibility, a reality where something exists in all forms at once. A particle is here and there, a spin is up and down, a system exists in multiple states. Until we look at it, only when we measure, does it choose one reality. This is quantum superposition, not just a weird effect, not just an illusion, but a core principle of quantum mechanics. That says nature only decides when we observe it. What is quantum superposition? The paradox asks, if a particle exists in multiple states at once, does that mean reality is just probability? If measuring forces it to choose, does that mean observation creates reality? If superposition is real, does that mean multiple versions of the universe exist at once? Different perspectives. Quantum superposition works because waves can exist in multiple forms. An electron is both a wave and a particle. It does not have a single position. It has many possibilities, until a measurement forces it to decide. If particles are in superposition, does that mean everything else is too? What if large objects could exist in multiple states? What if we were in superposition? Would that mean we live in multiple realities at once? If we master superposition, can we control quantum reality? What if we kept things in superposition longer? What if we never forced them to choose? Would we create new states of matter? Or would we still be limited by our own need to observe? 36 Schrödinger's cat paradox. A cat, a box, a reality where life and death exist together. Inside the box, a cat is trapped with a quantum device. If a particle decays, the cat dies. If it does not, the cat lives. But until we open the box, the cat is both alive and dead at the same time. This is Schrödinger's cat paradox, not just a thought experiment, not just a strange idea, but a challenge to our understanding of reality itself. What is Schrödinger's cat paradox? The paradox asks, if a quantum system exists in two states at once, does that mean reality only becomes real when we look at it? If observation determines the outcome, does that mean consciousness controls reality? If superposition applies to big objects, does that mean entire universes exist in multiple forms? Different perspectives. Schrödinger's cat shows the strangeness of quantum mechanics. A particle exists in superposition. A cat's fate depends on it. And suddenly, we must ask, when does reality decide? If observation determines reality, are we creating the world by looking at it? What if, before measurement, everything exists in all states at once? What if our awareness collapses possibilities into one? Would that mean we are shaping reality itself? If we keep the cat in superposition, do we create a quantum paradox? What if we never checked the box? What if we preserved uncertainty forever? Would that mean the cat is trapped between life and death indefinitely? Or would nature still find a way to decide the outcome? 37th, quantum entanglement. A connection, an instant link, a pair of particles. That seemed to defy space itself. Measure one, and the other reacts instantly, no matter how far apart they are. No signal, no delay, just pure quantum strangeness. This is quantum entanglement, not just a theory, not just a mystery, but a real effect that Einstein called spooky action at a distance. What is quantum entanglement? The paradox asks, if two particles can influence each other instantly, does that mean information travels faster than light? If entanglement is real, does that mean everything in the universe could be connected? If space does not matter in entanglement, does that mean space itself is an illusion? Different perspectives. Quantum entanglement works because it links particles beyond classical physics. A photon is split, two electrons interact, and suddenly, they share the same quantum state, even if they are light years apart. If entanglement exists, can we use it for instant communication? What if we could send messages using entanglement? What if we used it for quantum encryption? Would that mean a future of unhackable information? If everything was once connected in the Big Bang, are we all still entangled? What if every particle was once linked? What if the entire universe is still connected? Would that mean reality is just a giant quantum system? The truth about quantum entanglement. The paradox challenges our understanding of locality versus instant connection, information versus speed. Whether reality is separate or fundamentally intertwined. If entanglement ignores distance, does that mean space itself is meaningless? 38. The EPR paradox. A thought experiment. A challenge. A test of quantum reality. That left even Einstein puzzled. If quantum entanglement is real, then measuring one particle should instantly affect its twin. But how? Is information traveling faster than light? Or is reality predetermined before we observe it? This is the EPR paradox. Not just a question, not just an idea, but a fundamental crack in the way we understand physics. What is the EPR paradox? The paradox asks, if measuring one particle instantly affects another, does that mean hidden variables determine outcomes? If quantum mechanics is correct, does that mean reality is non-local? If measurement defines a system, does that mean the universe only exists when we observe it? Different perspectives. The EPR paradox works because it challenges the idea of objective reality. A particle's state is unknown. A measurement is made, and instantly, its entangled partner takes on a defined state. Was the outcome always determined, or did the act of measurement force the result? If quantum mechanics is correct, does that mean reality is non-local? What if distance does not matter? What if particles interact beyond space and time? Would that mean the universe is fundamentally connected at every level? If the EPR paradox can be resolved, will we finally understand reality? What if we discovered hidden variables? What if we proved quantum mechanics incomplete? Would we find a deeper truth? Or would we still be staring into an unknowable quantum mystery? 39th, quantum tunneling. A barrier, a wall, a quantum particle that passes through anyway. A wave moves forward, a potential barrier blocks its way. But instead of stopping, the wave bleeds through. A particle appears on the other side, even though it should not be able to cross. This is quantum tunneling. Not just a trick, not just a rare event, but a real phenomenon. That powers the sun and drives quantum technology. What is quantum tunneling? The paradox asks, if particles can pass through barriers, does that mean reality is not as solid as we think? If tunneling is possible, does that mean quantum objects ignore classical physics? If waves can spread through barriers, does that mean everything is a probability? Different perspectives. Quantum tunneling works because particles are also waves. An electron approaches a barrier. Its wave function spreads beyond it. and suddenly it appears on the other side, even though it never had the energy to cross. If tunneling is real, could we walk through walls? What if we increased the probability? What if we engineered matter to behave differently? Would that mean the future holds quantum teleportation? If tunneling powers nuclear fusion, does that mean the sun shouldn't exist? What if particles had to collide perfectly for fusion? What if the sun's energy was only possible because of quantum magic? Would that mean without tunneling the universe would be dark? 40th quantum probability and measurement. A wave, a choice, a reality that only exists when you observe it. Before measurement, a particle has no definite state. It is a probability wave. It is everywhere and nowhere, until you look, until you measure. And suddenly, it picks a state. It becomes real. This is quantum probability and measurement, not a guessing game, not uncertainty, but a fundamental truth about reality. That says, the act of observing shapes what is observed. What is quantum probability and measurement? The paradox asks, if a particle exists in many states before we measure it, does that mean reality is undefined until we observe it? If measurement collapses probability, does that mean reality is shaped by consciousness? If everything exists as a probability wave, does that mean the universe is made of mathematical possibilities? Different perspectives. Quantum probability works because reality is not fixed at small scales. A particle does not have one position. It has many possible positions, and when you measure, you pick just one. If observation creates reality, does that mean the universe needs an observer? What if no one looked? What if nothing was measured? Would the universe remain a cloud of infinite possibilities? If we control measurement, do we control reality? What if we delayed measurement? What if we manipulated the act of observation? Would we control which reality becomes real? Or would we still be limited by the rules of quantum mechanics? 41st, quantum computing, a qubit, a superposition, a machine that calculates in all possible states at once. A classical bit is 0 or 1. A quantum bit is 0 and 1. It processes multiple realities simultaneously. It solves problems in ways no normal computer can. This is quantum computing. Not just faster processors, not just smaller chips, but a completely new way to think about information. What is quantum computing? The paradox asks, if a quantum computer processes multiple states at once, does that mean it is thinking in parallel universes? If classical computers follow logic, does that mean quantum computers follow probability? If qubits can be entangled, does that mean a change in one affects the others instantly, no matter how far apart? Different perspectives. Quantum computing works because qubits exist in superposition. A classical bit is like a light switch, on or off. A quantum bit is like a wave, both on and off, and that means it can solve many problems at once. If quantum computing is so powerful, can it break encryption? What if it solved huge numbers instantly? What if it cracked every password? Would that mean security itself becomes impossible? If we build a true quantum computer, do we unlock new laws of physics? What if we simulated entire universes? What if we calculated beyond classical limits? Would we discover new physical laws? Or would we still be bound by the unknown rules of the quantum world? The truth about quantum computing. The paradox challenges our understanding of classical versus quantum thinking, logic versus probability, whether computation is just math or a gateway to deeper realities. If quantum computing processes many realities at once, does that mean it is thinking in parallel universes? 42. The many worlds interpretation. A measurement, a choice, a reality that splits instead of collapsing. In one world, the particle goes left. In another, it goes right. Both happen. Both exist. Both continue separately. Every quantum event creates a new universe. Every possibility is real somewhere. This is the many worlds interpretation. Not just a theory, not just speculation, but a radical idea that says every choice you could have made, you did, just in another world. What is the many worlds interpretation? The paradox asks, if every possibility creates a new universe, does that mean there are infinite versions of us? If nothing collapses but instead splits, does that mean all realities exist equally? If many worlds are real, does that mean death is just moving into another version of existence? Different perspectives. The many worlds. Interpretation works because it avoids the problem of measurement. In standard quantum mechanics, observation collapses a wave function. In many worlds, observation just creates a split. There is no collapse, only more universes. If many worlds exist, can we ever communicate with them? What if we found a way to interact? What if we moved between realities? Would that mean we could change choices we regret? Or would we still be forever trapped in just one branch? If many worlds are real, what does that say about free will? What if every choice creates a new timeline? What if every possibility exists somewhere else? Would that mean there is no single you? Or would it mean that every version of you is equally real? 43. The Copenhagen interpretation. A measurement. A collapse. A reality that does not exist until it is observed. A particle is a wave of possibilities. It has no definite position. It has no definite state until you look. Then, suddenly, it chooses one reality. This is the Copenhagen interpretation. Not just a theory, not just a guess, but a way to explain why quantum mechanics defies common sense. What is the Copenhagen interpretation? The paradox asks, if a particle only has a definite state when observed, does that mean reality is undefined until we look? If measurement collapses a wave into a particle, does that mean observation creates reality? If probability rules quantum physics, does that mean certainty is just an illusion? Different perspectives. The Copenhagen interpretation works because it matches experiments. A photon is a wave. A photon is a particle, until you measure it. Then it chooses one. If reality only exists when observed, what happens when no one is watching? What if the universe only solidifies when we look at it? What if everything remains undefined until it is measured? Would that mean reality is just a system waiting to collapse? If we control measurement, do we control reality? What if we chose when to collapse the wave? What if we forced the universe to pick a state? Would we shape reality? Or would we still be trapped in a quantum world of probabilities? 44. The role of observation in quantum mechanics. A glance, a measurement, a reality that depends on awareness. A particle is in many places at once. A particle follows all paths until an observer checks. Then, suddenly, the infinite becomes one choice. This is the role of observation in quantum mechanics. Not just a question, not just philosophy, but a mystery that suggests that looking at reality may change it forever. What is the role of observation in quantum mechanics? The paradox asks, if observation changes a quantum state, does that mean reality depends on being watched? If measuring a system alters it, does that mean we can never truly see the original state? If quantum mechanics reacts to observers, does that mean consciousness is part of physics? Different perspectives. Observation affects reality. Because measurement changes the system. A particle behaves one way. Then, you observe it, and suddenly, it acts differently. Because in the quantum world, looking is part of the equation. If reality is affected by observation, does that mean we create it? What if we are not just passive watchers? What if our awareness forces the universe to take shape? Would that mean the act of seeing is the act of creating reality? If we could measure without interfering, could we see the true nature of reality? What if we found a way to observe without touching? What if we looked without collapsing the wave? Would we finally see reality before it makes a choice? Or would we still find that the act of watching changes the outcome? 45. The anthropic principle. A universe, a pattern, a reality that seems perfectly designed for life. The laws of physics just happen to allow stars to form. Gravity just happens to be strong enough for planets. The nuclear forces just happen to make atoms stable. And suddenly, it feels like the universe was made for us. This is the anthropic principle. Not just coincidence, not just statistics, but a question of whether the universe was fine-tuned for life, or if life simply adapted to the universe. What is the anthropic principle? The paradox asks, if the universe is fine-tuned for life, does that mean it was created with purpose? If the physical constants were slightly different, does that mean we would not exist at all? If life only exists because the universe allows it, does that mean our existence is just a cosmic accident? Different perspectives. The anthropic principle works because we can only observe a universe that supports life. If the universe had different rules, we would not be here to ask the question. That is why our existence feels special, because in any reality where life exists, it must have been possible for life to arise. If the universe is fine-tuned for life, does that mean there is a creator? What if the laws of physics were chosen? What if someone or something set the constants perfectly? Would that mean the universe was built for us? If there are infinite universes, is this just one that happens to work? What if there are billions of universes? What if most are dead and lifeless? Would that mean we live in one that just happens to allow life? Or is there something deeper behind the fine-tuning? 46. The holographic principle. A surface, a projection, a reality that might be a shadow of something deeper. A black hole's information is stored on its surface. A universe's information might be encoded on a distant boundary. What if everything inside is just a hologram? This is the holographic principle, not just a theory, not just a possibility, but a radical idea that suggests the universe is two-dimensional at its core. What is the holographic principle? The paradox asks, if everything inside a black hole is encoded on its surface, does that mean our reality is just a projection? If information is preserved at the edges of the universe, does that mean space is just a mathematical illusion? If the universe is a hologram, does that mean everything we experience is a lower dimensional reality? Different perspectives. The holographic principle works because information is key. A black hole's entropy is measured by its surface area. A hologram contains a 3D image on a 2D sheet. And suddenly, physics suggests space itself might work the same way. If we are living in a hologram, what is the real universe? What if the true universe exists outside our perception? What if our 3D world is just data encoded on a distant horizon? Would that mean reality is a projection? If the holographic principle is true, can we ever escape the illusion? What if space itself is a trick of perception? What if time and matter are just emergent properties? Would we ever see beyond the screen? Or would we still be trapped in the illusion of depth? 47. The multiverse theory. A choice, a split, a universe where every possibility exists. You take one path, another you takes a different one. Every decision creates a new reality. Every event spawns countless parallel worlds. Some are nearly identical, some are completely alien, and suddenly, reality is not singular. It is a vast branching network of infinite possibilities. This is the multiverse theory, not just science fiction, not just a fantasy, but a serious cosmological question. That suggests our universe is just one of many. What is the multiverse theory? The paradox asks, if every choice creates a new universe, does that mean there are infinite versions of you? If the multiverse is real, does that mean every possible history has already happened? If there are infinite worlds, does that mean the universe we know is just one tiny fragment of reality? Different perspectives. The multiverse theory works because quantum mechanics suggests probabilities exist in superposition. A quantum particle exists in many states. An observer collapses reality into one outcome, and suddenly, every possibility might be equally real in different timelines. If the multiverse exists, can we ever travel between universes? What if we could shift from one timeline to another? What if we could find another version of ourselves? Would we learn from them? Or would we break reality by interacting with them? If infinite universes exist, does that mean nothing is truly unique? What if every story, every dream, every nightmare already exists somewhere? Would that mean everything that can happen has happened? Or would we still feel like our choices matter? 48. The Many Worlds Interpretation, MWI. A wave, a measurement, a moment where the universe splits. A quantum particle exists in many states at once until you observe it, and when you do, reality branches. One world where the particle is here, another where it is there. One world where you turn left, another where you turn right. Because in this interpretation, every possibility is real. This is the many worlds interpretation, not just speculation, not just philosophy, but a serious alternative to quantum collapse. That suggests measurement does not choose a reality, it creates all of them. What is the many worlds interpretation? The paradox asks, if every quantum outcome creates a new universe, does that mean there is no single true reality? If the universe splits every time an event happens, does that mean time is an endless branching tree? If we exist in countless versions, does that mean consciousness is fragmented across infinite realities? Different perspectives. The many worlds. Interpretation works because it avoids the problem of wave function collapse. A particle exists in all states. An observer does not force it to choose. Instead, the universe just splits into one where each outcome happens. If many worlds exist, can we ever communicate between them? What if we could reach across realities? What if we could merge timelines? Would we learn from our other selves? Or would we destroy the fragile balance of existence? If everything that can happen does happen, do we have free will? What if every decision creates new versions of us? What if every possibility exists somewhere? Would that mean 49th, bubble universes and eternal inflation, a space, a boundary, a universe that is not alone? The Big Bang did not just happen once, it happened again and again. New universes bubble into existence. Some expand, some collapse, some follow different laws of physics, and somewhere, right now, a new universe is being born. This is bubble universes and eternal inflation, not just speculation, not just imagination, but a theory that suggests the cosmos never truly stops expanding. What are bubble universes and eternal inflation? The paradox asks, if new universes keep forming, does that mean our universe is just one of many? If inflation never stops, does that mean creation is an ongoing process? If some universes die while others form, does that mean the multiverse is infinite? Different perspectives. Eternal inflation works because space never fully stabilizes. A quantum fluctuation triggers expansion. A new universe forms, and somewhere else. The same process happens again. If there are infinite universes, could we ever travel between them? What if we found a way to connect bubbles? What if wormholes linked different realities? Would we visit other universes? Or would each bubble be forever isolated? If universes are born and die, What came before everything? What if time never had a beginning? What if existence always was? Would that mean there was never a first universe? The truth about bubble universes and eternal inflation. The paradox challenges our understanding of creation versus eternity, expansion versus boundaries. Whether the multiverse is infinite or just another stage in an even larger system, if universes keep forming, does that mean reality itself has no limits? 50. The brain multiverse. A dimension, a layer, a reality beyond our perception. We live in 3 dimensions. But what if higher dimensions exist? What if our universe is a membrane, floating in a higher dimensional space? And what if other universes are floating right beside us? This is the brain multiverse, not just parallel worlds, not just a theory, but a suggestion that our universe is just one of many dimensions, stacked like pages in a book. What is the brain multiverse? The paradox asks, if our universe is a membrane, does that mean we could interact with other universes? If extra dimensions exist, does that mean we are limited by what we can see? If gravity leaks between brains, does that mean some universal forces are shared? Different perspectives. The brain multiverse works because it explains hidden dimensions. A brain floats in higher space. Another brain moves beside it. And sometimes they collide, creating a new Big Bang. If other brains exist, could we ever see them? What if we sent a signal through higher dimensions? What if gravity revealed hidden brains? Would we glimpse other realities, or would they remain forever invisible? If universes are brains, what holds them together? What if higher dimensional forces control them? What if brains are just shadows of something deeper? Would we ever understand the full structure of existence? 51. The mathematical multiverse. An equation, a pattern, a universe defined by pure mathematics. We see physics, we see matter, we see energy. But beneath it all, there is only math. Numbers do not describe reality. Numbers are reality. Every possibility exists, because every equation that can exist does exist. This is the mathematical multiverse, not just speculation, not just a metaphor, but a theory that suggests reality is nothing more than a self-consistent mathematical structure. What is the mathematical multiverse? The paradox asks, if the universe follows mathematical laws, does that mean reality is just a set of equations? If math describes reality perfectly, does that mean the physical world is an illusion? If every equation that can exist corresponds to a real universe, does that mean everything possible exists somewhere? Different perspectives. The mathematical multiverse works because it explains why the universe is logical. The laws of physics are mathematical equations. The patterns of galaxies follow fractals. The quantum world behaves like a probability function. And suddenly, reality is just an enormous math problem. If reality is just math, could we simulate entire universes? What if we wrote the equations of a new universe? What if our own universe was just a simulation running in a higher system? Would that mean we are just numbers in a cosmic equation? If everything that can exist must exist, what does that mean for free will? What if every decision we make already exists in another mathematical universe? What if every possibility is already written in numbers? Would that mean free will is just an illusion? 52. The information paradox. A collapse. A mystery. A paradox hidden in the heart of black holes. Matter falls in. Light cannot escape. But what happens to information? Does it vanish forever? Quantum mechanics says information cannot be lost. General relativity says black holes erase it. Both cannot be true. This is the information paradox, not just a puzzle, not just a debate, but a fundamental clash between quantum physics and gravity. What is the information paradox? The paradox asks, If information falls into a black hole and disappears, does that mean the laws of physics are broken? If information is preserved in quantum mechanics, does that mean black holes must somehow return it? If black holes truly erase data, does that mean the universe can forget the past? Different perspectives. The information paradox exists because two theories clash. Quantum physics says information is never lost. General relativity says black holes destroy it. And if both are true, something deeper is missing. If information is preserved, where does it go? What if it is stored in the event horizon? What if it is leaked out through radiation? Would that mean black holes are not truly black? If we solve the information paradox, do we unlock a new theory of physics? What if we find the missing link? What if we unify gravity and quantum mechanics? Would we discover the ultimate laws of the universe? Or would we still be left with deeper mysteries? 53rd, Hawking radiation and black hole. Thermodynamics, a discovery, a prediction, a way for black holes to die. Black holes are not eternal. They do not last forever. They leak radiation, they lose mass. They slowly shrink and vanish, because empty space is not empty, because quantum effects create pairs of particles. One falls in, one escapes, and the black hole evaporates. This is Hawking radiation. Not science fiction, not a wild guess, but a mathematical consequence of quantum mechanics near black holes. What is Hawking radiation? The paradox asks, if black holes emit radiation, does that mean they slowly disappear? If quantum effects create Hawking radiation, does that mean space itself is full of hidden energy? If black holes evaporate, does that mean some black holes are already gone? Different perspectives. Hawking radiation works because empty space is not truly empty. Even in a vacuum, particles appear and disappear. Even in deep space, fluctuations create energy. And near a black hole, some of those particles escape forever. If black holes evaporate, what happens to the information inside? What if the black hole shrinks completely? What if all the information is lost with it? Would that mean physics is broken? If we harness Hawking radiation, could we use black holes for energy? What if we captured the radiation? What if we fed a black hole to extend its life? Would we create the ultimate power source? Or would we still be chasing impossible physics? 54. The firewall hypothesis. A barrier, a wall of energy, a burning boundary. That might exist at the edge of a black hole. General relativity says, falling into a black hole feels normal, until the singularity. Quantum physics says, information cannot be lost, but the event horizon destroys it. If both are true, there must be a firewall, a region of pure energy, a point of no return, where anything that crosses is instantly burned away. This is the firewall hypothesis, not yet proven, not yet resolved, but a controversial idea that could rewrite what we know about black holes. What is the firewall hypothesis? The paradox asks, if firewalls exist, does that mean black holes are surrounded by walls of pure energy? If relativity says falling into a black hole is smooth, does that mean firewalls break Einstein's theory? If quantum physics demands a firewall, does that mean space-time is not continuous? Different perspectives. Firewalls might exist because information needs to be destroyed. If information cannot escape, if black holes do not leak it out, then something must erase it. And that something could be a firewall. If firewalls exist, do they destroy the idea of a smooth space-time? What if event horizons are violent? What if falling into a black hole is instant death? Would that mean Einstein's vision of gravity is incomplete? If we prove firewalls exist, do we finally solve the information paradox? What if firewalls hold the lost information? What if black holes encode everything at the edge? would we discover the true nature of space and time? Or would we still be left with even deeper mysteries? 55th, black hole. Singularities and event horizons. A collapse, a mystery, a place where physics breaks down, a massive star dies, and space curves infinitely. Gravity grows stronger until nothing can escape. A boundary forms, a line that once crossed means no return. This is black hole singularities and event horizons, not just a region, not just an edge, but a limit in space-time, where the laws of physics cease to function. What are black hole singularities and event horizons? The paradox asks, if a singularity is infinitely dense, does that mean space can truly collapse? If nothing escapes the event horizon, does that mean we can never see inside a black hole? If physics breaks at singularities, does that mean our understanding of reality is incomplete? Different perspectives. Black hole singularities exist because gravity can overwhelm space-time. A star collapses, a point of infinite density forms, and suddenly, space-time tears itself apart. If nothing can escape the event horizon, can anything ever be retrieved? What if information is lost forever? What if black holes erase reality? Would that mean the past could vanish without a trace? If we could understand singularities, would we understand the universe itself? What if singularities hide deeper physics? What if they are gateways to new dimensions? Would we finally uncover the final secrets of space-time? The truth about black hole, singularities and event horizons. The paradox challenges our understanding of space versus collapse, gravity versus information. Whether singularities are truly real or just the result of physics we do not yet understand. If nothing escapes the event horizon, does that mean black holes are places where the past can disappear forever? 56. The Wheeler-DeWitt equation. A wave function, a theory, an attempt to describe everything at once. Quantum mechanics explains the smallest scales. General relativity describes the largest structures. But gravity does not fit into quantum mechanics, and quantum mechanics does not fit into gravity. Can one equation unify them? This is the Wheeler-DeWitt equation, not just a mathematical trick, not just a model, but an equation that tries to describe the wave function of the universe itself. What is the Wheeler-DeWitt equation? The paradox asks, if time disappears in this equation, does that mean time is not fundamental? If the universe has a wave function, does that mean it behaves like a quantum system? If we solve this equation, do we finally unify quantum mechanics and gravity? Different perspectives. The Wheeler-DeWitt equation tries to solve the quantum gravity puzzle. Quantum mechanics rules particles. General relativity rules space-time. But no one knows how to make them work together. If time disappears in this equation, does that mean time is an illusion? What if time emerges from quantum states? What if the past and future exist all at once? Would that mean time is just a human perception? If we understand this equation, do we finally understand the universe? What if we solved it? What if we truly understood how gravity and quantum mechanics fit together? Would we unlock the theory of everything? Or would we still be searching for deeper mysteries? 57th, quantum gravity basics. A bridge, a paradox, a missing link between two great theories. Quantum mechanics describes particles and forces. General relativity describes space and time. But where they meet, everything falls apart. A black hole forms. And quantum effects do not fit into curved space-time. Gravity is too weak to act like the other fundamental forces. This is quantum gravity basics. Not just a problem, not just a mystery, but the deepest puzzle in modern physics. What is quantum gravity? The paradox asks, if quantum mechanics and general relativity cannot be combined, does that mean one of them is incomplete? If gravity is different from other forces, does that mean it is not truly a force at all? If we solve quantum gravity, do we finally unlock the nature of space-time itself? Different perspectives. Quantum gravity is needed because space-time must obey quantum rules. A particle is uncertain, a wave function spreads, but space-time must be smooth. Something does not fit. If gravity is not a force, could it be something deeper? What if gravity emerges from quantum entanglement? What if space itself is built from information? Would that mean gravity is not a fundamental force? If we understand quantum gravity, do we finally understand reality? What if we unified all forces? What if we discovered what space-time is really made of? Would we finally reach the ultimate theory of the universe, or would we still be searching for the next great discovery? 58th, string theory. Fundamentals: a vibration, a frequency, a world where particles are not points, but tiny strings. They vibrate, they oscillate, they define mass, charge, and force. Electrons, quarks, and photons are just different notes on the same cosmic string. And suddenly, the universe is not made of particles, it is made of music. This is string theory, not just a model, not just an idea, but a potential key to the fundamental nature of reality. What is string theory? The paradox asks, if everything is made of strings, does that mean reality is just a vibration? If strings explain all forces, does that mean we have found the theory of everything? If particles are just different string vibrations, does that mean mass, charge, and spin are just musical notes? Different perspectives. String theory works because it unifies all forces: gravity, electromagnetism, the strong and weak nuclear forces, all of them, might just be different vibrations of strings. If strings exist, why can't we detect them? What if they are too small? What if they vibrate in dimensions we cannot see? Would that mean we are blind to the true structure of the universe? If we understand strings, can we control reality? What if we could change a vibration? What if we could rewrite the frequency of matter itself? Would we become architects of the universe? Or would we still be searching for the ultimate truth? The truth about string theory. The paradox challenges our understanding of particles versus waves, matter versus vibration, whether reality is just a set of hidden harmonics. If everything is just a string vibrating, does that mean the universe is a cosmic symphony waiting to be understood? 59th. Extra dimensions in string theory. A space, a fold, a hidden dimension that we cannot see. We move in 3 dimensions. We live in 4 with time. But what if reality has 10 or even 11? What if extra dimensions are curled up, too small to notice? This is extra dimensions in string theory, not science fiction, not speculation, but a mathematical necessity to make the universe work. What are extra dimensions in string theory? The paradox asks, if extra dimensions exist, why don't we perceive them? If reality has more than 4 dimensions, does that mean we are trapped in a lower dimensional space? If forces move through extra dimensions, does that mean gravity is leaking into them? Different perspectives. Extra dimensions exist because they solve the equations. String theory needs extra dimensions. Without them, the math breaks down. And suddenly, reality is bigger than we imagined. If we could see extra dimensions, what would reality look like? What if we lived in 5-dimensional space? What if time had more than one direction? Would that mean we could see alternate realities overlapping our own? If extra dimensions are real, can we travel through them? What if we could fold space? What if we could slip through unseen pathways? Would we unlock shortcuts across the universe? Or would we still be trapped in our 3-dimensional prison? 60th. M-theory and brain worlds. A membrane. A universe. A world that is not floating in space, but sitting on a higher dimensional brain. In string theory, there are not just strings, there are membranes, brains, and our universe could be just one brain among many, parallel realities, floating worlds, hidden universes that exist just out of reach. This is M theory and brain worlds, not just an extension of string theory, not just a new model, but a radical shift in how we see existence itself. What is M theory and brain worlds? The paradox asks, if our universe is on a brain, does that mean other universes exist next to us? If gravity can leak between brains, does that mean dark matter could be the pull of another universe? If brains collide, does that mean the Big Bang was just a brain collision? Different perspectives. M theory works because it unifies string theories. 5 competing string theories, all of them incomplete. But when viewed from a higher perspective, they are all part of one bigger theory. And suddenly, string theory makes sense. If brain worlds exist, could we ever travel to another universe? What if brains are stacked together? What if another universe is just a millimeter away, but in a dimension we cannot reach? Would that mean there is a way to cross over? If we understand M theory, do we unlock the secrets of the cosmos? What if brain interactions created our Big Bang? What if gravity is stronger in other universes? Would that mean everything we know is just a fragment of a much larger reality? Or would we still be searching for the final answer? 61st, loop quantum gravity. A theory, a structure, a vision of space-time made of tiny loops. In general relativity, space is smooth. In quantum mechanics, everything is discrete. What if space itself was woven from microscopic loops of energy? What if gravity was not a force, but the result of these loops interacting? This is loop quantum gravity, not just an alternative to string theory, not just another idea, but a possible answer to the mystery of quantum gravity. What is loop quantum gravity? The paradox asks, if space is made of loops, does that mean space is not continuous? If time emerges from quantum structures, does that mean time itself is not fundamental? If space-time is built from loops, does that mean black holes and singularities do not truly exist? Different perspectives. Loop quantum gravity works because it quantizes space. No infinite smooth curves, no continuous space-time, just tiny loops forming reality. If space has a quantum structure, does that mean time could be reversible? What if time was just another effect of these loops? What if rewiring the loops let us move forward and backward in time? If we prove loop quantum gravity, do we finally unify physics? What if we found the missing link? What if loop quantum gravity explained everything? Would we finally see the universe for what it really is? Or would we still be searching for deeper answers? The truth about loop quantum gravity. The paradox challenges our understanding of space versus discreteness, gravity versus quantum interactions, whether space-time is continuous or just another quantum effect. If space is made of loops, does that mean the universe itself is woven from something deeper than reality? 62. The problem of time in quantum mechanics. A clock, a measurement, a contradiction between two worlds. In general relativity, time is a flexible dimension. In quantum mechanics, time is just a parameter. One sees time as a flowing river. The other sees it as an unchanging stage. Which one is right? This is the problem of time in quantum mechanics. Not just a philosophical debate, not just an issue for equations, but a fundamental clash between the two greatest theories of physics. What is the problem of time in quantum mechanics? The paradox asks, if time is absolute in quantum mechanics but relative in relativity, which one is correct? If time is just a parameter in quantum physics, does that mean it is not real? If time emerges from deeper laws, does that mean it is an illusion created by human perception? Different perspectives. Time works differently in different theories. In relativity, Time is woven into space. In quantum mechanics, time is just an external clock. So how do we merge the two? If time is not fundamental, what does that mean for our understanding of reality? What if time emerges from quantum entanglement? What if we experience time only because we are inside the system? Would that mean the universe has no true past or future? If we solve the problem of time, do we solve quantum gravity? What if the key to uniting physics was hidden in how we understand time? What if time was the missing link between quantum mechanics and relativity? Would we finally have a theory of everything? Or would we still be trapped by our own perception? 63. The standard model of particle physics. A chart, a classification, a map of all known particles, electrons, quarks, neutrinos, bosons. Each one plays a role. Each one follows specific rules. And together, they form the fundamental building blocks of the universe. This is the standard model of particle physics, not just a theory, not just a collection of particles, but the closest thing we have to a complete blueprint of reality. What is the standard model of particle physics? The paradox asks, if the standard model explains all known particles, does that mean we understand the universe completely? If the Higgs boson gives mass, does that mean mass is not an inherent property of particles? If there are missing pieces, does that mean physics is still incomplete? Different perspectives. The standard model works because it predicts particle behavior. Every force, every fundamental particle, every interaction fits into this beautiful framework. If the standard model is complete, why do we need new physics? What if dark matter is not included? What if gravity is missing from the model? Would that mean we are only seeing part of the picture? If we discover new particles, do we need a new model? What if physics keeps evolving? What if we find new forces, new particles, new rules? Would we abandon the standard model? Or would we simply expand it to fit the deeper truths of the universe? 64th quarks and leptons, a particle, a building block, a world that is smaller than atoms, yet holds the universe together. Protons and neutrons are not fundamental. They are made of quarks. Electrons orbit atoms, but they are part of the lepton family. 2 families, 6 types each, the foundation of everything we see. This is quarks and leptons, not just subatomic particles, not just small fragments, but the true building blocks of reality. What are quarks and leptons? The paradox asks, if quarks and leptons are fundamental, does that mean nothing is smaller than them? If quarks always combine into larger particles, does that mean they are never truly independent? If leptons move freely, does that mean they are the simplest possible particles? Different perspectives. Quarks and leptons work because they form the foundation of matter. A proton is 2 up quarks and 1 down quark. A neutron is 2 down quarks and 1 up quark. A lepton, like an electron, moves freely, and suddenly, everything in physics makes sense. If quarks cannot exist alone, do they have a deeper structure? What if quarks are made of something smaller? What if leptons hide an unknown structure? Would that mean the universe has an even deeper layer? If we could manipulate quarks and leptons, could we reshape matter? What if we rearranged quarks into new particles? What if we controlled how leptons behaved? Would we create new forms of matter? Or would we still be bound by the laws of the standard model? 65. The role of force carrier particles. A push, a pull, a force that moves through invisible particles. Gravity pulls objects together. Electromagnetism attracts and repels charges. The strong force holds atomic nuclei together. The weak force controls radioactive decay. But how do they work? They exchange force carrier particles. This is the role of force carrier particles, not just invisible messengers, not just theoretical concepts, but the reason forces exist at all. What are force carrier particles? The paradox asks, if forces are carried by particles, does that mean they are not continuous? If force carriers are real, does that mean forces are physical objects? If particles transfer force, does that mean nothing truly touches anything else? Different perspectives. Force carrier particles work because they explain interaction. A photon carries the electromagnetic force, a gluon carries the strong force, a W and Z boson carry the weak force, and suddenly, forces are not just invisible fields, they are physical exchanges of energy. If force carriers exist, does that mean gravity should have one too? What if there is a graviton? What if gravity is not just curved space-time? Would that mean we could one day quantize gravity? If we could manipulate force carriers, could we control forces? What if we altered the way photons interact? What if we modified the strong nuclear force? Would we break the laws of physics? Or would we still be missing a deeper understanding of reality? The truth about force carrier particles. The paradox challenges our understanding of forces versus particles, fields versus physical interactions, whether forces are truly continuous or just a series of discrete exchanges. If all forces come from particles, does that mean the universe is built from tiny interactions we cannot see? 66. The Higgs boson and the Higgs field. A mass, a mystery, a field that gives substance to everything. Particles move through the Higgs field, and they gain mass. No Higgs field, no mass, no stars, no planets, no life. This is the Higgs boson and the Higgs field. Not just a discovery, not just a Nobel Prize, but the reason the universe has structure. What is the Higgs boson and the Higgs field? The paradox asks, if mass comes from the Higgs field, does that mean mass is just resistance to movement? If the Higgs boson gives particles mass, does that mean it controls reality? If the Higgs field were turned off, would everything become massless? Different perspectives. The Higgs field works because it explains why particles have mass. A photon moves through space with no mass. A quark moves through the Higgs field and gains mass, and suddenly, mass is not a fundamental property. It is a side effect of interaction. If the Higgs field can be manipulated, can we change mass? What if we altered the Higgs field? What if we controlled the interaction of particles with it? Would we create massless matter? Would we make objects weigh less or more at will? If the Higgs field is everywhere, does that mean it shapes the universe? What if the Higgs field is connected to dark energy? What if it affects cosmic expansion? Would that mean the Higgs boson is more than just mass? Would it mean it controls the fate of the cosmos itself? 67. The hierarchy problem in particle physics. A force, a scale, a question that physics cannot yet answer. Gravity is weak, the strong force is strong. Electromagnetism is somewhere in between. But why? Why is gravity billions of times weaker than the forces that hold atoms together? Why does nature have such extreme differences in fundamental interactions? This is the hierarchy problem. Not just a puzzle, not just an observation, but one of the biggest mysteries in modern physics. What is the hierarchy problem? The paradox asks, if the fundamental forces all come from the same universe, why do they have such drastically different strengths? If gravity is so weak, does that mean extra dimensions or hidden particles are diluting its power? If we solve the hierarchy problem, does that mean we finally understand the deep structure of reality? Different perspectives. The hierarchy problem exists because physics has no answer yet. Gravity barely interacts with atoms. The strong force holds everything together, and no one knows why. If extra dimensions exist, could they be weakening gravity? What if gravity spreads into another dimension? What if it is strong elsewhere, but weak in our reality? Would that mean the universe is bigger than we think? If we solve the hierarchy problem, do we unlock new forces? What if we adjusted the strengths of fundamental interactions? What if we tuned physics like an instrument? Would we gain new forces, new particles, and new technologies? Or would we still be trapped in a reality that hides its deepest secrets. 68. The weak and strong nuclear forces. A bond, a decay, a force that shapes every atom in the universe. The strong force holds atomic nuclei together. The weak force causes radioactive decay. Without them, atoms would fall apart, stars would not burn, and the universe would never have formed. This is the weak and strong nuclear forces, not just fundamental forces, not just invisible interactions, but the reason matter is stable and the universe continues to evolve. What are the weak and strong nuclear forces? The paradox asks, if the strong force is the strongest, why does it only act over tiny distances? If the weak force changes particles, does that mean atoms are not truly stable? If nuclear forces govern the universe, does that mean everything is shaped by interactions we can never directly see? Different perspectives. The strong force works because it binds quarks together. It holds protons and neutrons. It stops atoms from falling apart. It is powerful, but only at tiny distances. The weak force works because it allows the universe to evolve. It causes radioactive decay. It lets stars burn hydrogen into helium. And without it, there would be no fusion, no energy, no life. If we master nuclear forces, do we control the fundamental building blocks of matter? What if we stabilized unstable atoms? What if we harnessed nuclear power without danger? Would we gain limitless energy? Or would we still be bound by the limits of natural physics? 69. The Pauli exclusion principle. An atom, an electron, a rule that prevents everything from collapsing into chaos. Two electrons cannot occupy the same quantum state. Two particles cannot have identical properties, because if they could, atoms would collapse into a single mass. Matter would lose all structure, and the universe would be a featureless cloud of energy. This is the Pauli exclusion principle, not just a restriction, not just a rule, but the reason why matter has form, shape, and structure. What is the Pauli exclusion principle? The paradox asks, if electrons were not restricted, would all matter collapse into a single dense blob? If this rule keeps electrons apart, does that mean structure is just a quantum effect? If atoms obey the exclusion principle, does that mean all matter is governed by invisible quantum laws? Different perspectives. The Pauli exclusion principle works because it organizes matter. Electrons stack into shells, atoms form into stable elements, and without it, everything would be a formless mess. If this rule did not exist, would the universe still be recognizable? What if electrons could overlap? What if atoms could collapse? Would anything still have shape? Or would we live in a universe of pure quantum chaos? If we could bypass the exclusion principle, could we create new states of matter? What if we forced electrons into identical states? What if we created new exotic materials? Would we discover strange new forms of physics? Or would we break the fundamental rules of the quantum world? 70th Quantum Chromodynamics, QCD. A force, a bond, a hidden interaction that holds matter together. Inside every proton and neutron, quarks move. They are bound together by gluons. The force is strong, so strong that quarks can never be isolated. Pull them apart, and more energy appears, creating new quarks. This is quantum chromodynamics, QCD. Not just a theory, not just a force, but the fundamental glue of the universe. What is quantum chromodynamics, QCD? The paradox asks, if quarks can never be separated, does that mean they are permanently trapped? If energy turns into mass when quarks are pulled apart, does that mean mass is just another form of energy? If gluons hold everything together, does that mean the universe is fundamentally bound by invisible forces? Different perspectives. QCD works because the strong force grows stronger with distance. Try to pull quarks apart, and the force increases. Instead of breaking, new quarks form. So protons and neutrons never fall apart. If QCD prevents free quarks, What happens in extreme conditions? What if matter was heated to trillions of degrees? What if quarks were free for a moment? Would that mean a glimpse into the early universe? If we master QCD, could we unlock unlimited energy? What if we harnessed gluons? What if we controlled the strong force? Would we extract energy beyond imagination? Or would we still be limited by the laws of physics? The truth about quantum chromodynamics, QCD. The paradox challenges our understanding of particles versus forces, energy versus mass. Whether the strong force is just a deeper layer of reality we do not yet fully understand, if the strong force never lets go, does that mean the fundamental building blocks of the universe can never truly be free? 71st, Quantum Field Theory, QFT. A vibration, a fluctuation, a universe made of fields, not particles. Electrons are not tiny dots. They are excitations of the electron field. Photons are not flying particles. They are ripples in the electromagnetic field. All forces, all particles, all of reality is just a collection of interacting quantum fields. This is quantum field theory, QFT. Not just quantum mechanics, not just relativity, but the most fundamental description of nature we have. What is quantum field theory, QFT? The paradox asks, if everything is a field, does that mean particles do not truly exist? If fields vibrate to create mass, does that mean reality is just an interplay of waves? If QFT governs all interactions, does that mean space is never truly empty? Different perspectives. Quantum field theory works because it unifies forces and particles. Gravity is a field. Electromagnetism is a field. Matter itself is just excitations in a quantum field. And suddenly, everything is connected. If particles are just vibrations, does that mean reality is made of waves? What if we removed particles entirely? What if we saw reality as just energy ripples? Would that mean everything is just patterns in an invisible ocean? If we control quantum fields, do we control matter itself? What if we could tune the quantum fields? What if we could reshape mass and energy? Would we build new forms of matter? Or would we still be bound by deeper cosmic laws? 72. The vacuum energy and virtual particles. A void, an emptiness, a space that is never truly empty, even in a perfect vacuum. Particles appear, they exist for a moment, then vanish again. They borrow energy, then pay it back. And this happens everywhere, all the time. This is vacuum energy and virtual particles, not speculation, not science fiction, but a proven reality that shapes the universe at the smallest scales. What is the vacuum energy and virtual particles? The paradox asks, if empty space has energy, does that mean true nothingness does not exist? If particles can appear and disappear, does that mean energy can come from nowhere? If virtual particles affect real forces, does that mean the quantum world is constantly influencing reality? Different perspectives. Vacuum energy works because the quantum world is never still. Even in space devoid of matter, tiny fluctuations keep happening. Particles pop in and out of existence, and energy never fully reaches zero. If virtual particles exist, could we extract energy from the vacuum? What if we harnessed these fluctuations? What if we built machines that tapped into the quantum sea? Would that mean infinite energy hidden in the fabric of space? If empty space is not truly empty, what else is hiding there? What if space itself is a field? What if the vacuum holds hidden dimensions? Would we discover that the universe is far more populated than we ever imagined? 73. The Casimir effect. A vacuum, an empty space, a force that should not exist, but still does. Two metal plates sit close together, no charge, no force, yet they pull toward each other, because even in a vacuum, quantum fields never truly vanish. This is the Casimir effect, not just an anomaly, not just a prediction, but proof that empty space is never truly empty. What is the Casimir effect? The paradox asks, if a vacuum is empty, how can it create force? If quantum fluctuations exist everywhere, does that mean space itself has energy? If the vacuum contains energy, does that mean we could harness it for unlimited power? Different perspectives. The Casimir effect works. Because quantum fields are always active, space is never truly zero. Energy is always fluctuating. Even nothingness is something. If empty space creates forces, can we extract energy from the vacuum? What if we built devices to harness it? What if vacuum energy could be tapped like a fuel source? Would that mean infinite energy is real? If the vacuum has energy, what else could be hiding in empty space? What if particles appear and disappear in the void? What if entire universes bubble up from nothing? Would that mean reality itself emerges from a deeper quantum structure? The truth about the Casimir effect. The paradox challenges our understanding of vacuum versus energy, nothingness versus fluctuation, whether space itself is a source of hidden power. If quantum fields fill the vacuum, does that mean empty space is not truly empty? 74. The role of symmetry in physics. A pattern, a balance, a universe that follows perfect rules. Until symmetry is broken, particles interact, forces behave predictably, until something changes. And suddenly, new laws emerge, new properties appear. Because symmetry is the foundation of physics. This is the role of symmetry in physics. Not just beauty, not just mathematics, but the key to understanding why reality behaves as it does. What is the role of symmetry in physics? The paradox asks, if physics follows symmetry, does that mean the universe is built on perfect balance? If breaking symmetry creates new forces, does that mean reality emerges from imperfection? If symmetry governs the laws of nature, does that mean everything can be predicted? Different perspectives. Symmetry works because it creates predictability in physical laws. A spinning particle stays the same. A mirror reflection follows a rule. A force acts identically across space because symmetry governs everything. If symmetry is broken, does that mean nature is imperfect? What if forces split from an original one? What if particles change properties over time? Would that mean the universe evolved from a more symmetric past? If we fully understand symmetry, could we recreate the universe? What if we restored lost symmetries? What if we built perfect balance into physics? Would that mean we could design new laws of reality? The truth about the role of symmetry in physics. The paradox challenges our understanding of order versus imperfection, forces versus symmetry breaking. Whether physics is built on balance or the disruption of it. If the universe began in perfect symmetry, does that mean existence itself is the result of a broken balance? 75. The principle of least action. A motion, a decision, a law that says nature always finds the simplest path. A light beam travels, a planet orbits, an object moves, and in every case, it follows the path that minimizes effort. This is the principle of least action, not just a shortcut, not just an idea, but a fundamental rule of physics. That governs everything from mechanics to quantum fields. What is the principle of least action? The paradox asks, if the universe always follows the path of least action, does that mean everything is optimized? If action is minimized, does that mean physics behaves like an intelligent system? If nature always takes the simplest path, does that mean the future is already decided? Different perspectives. The principle of least action works because it describes efficient motion. A bouncing ball follows the shortest curve. A ray of light bends to take the fastest route. A particle travels as if it knew its entire journey in advance, because nature chooses efficiency. If the universe finds the simplest path, does that mean it has a purpose? What if physics acts as if it knows where it is going? What if action minimization is a deeper rule of reality? Would that mean the universe is not random, but intelligently structured? If we control the paths of least action, do we control the future? What if we could reshape the shortest paths? What if we altered space so that energy moved differently? Would we control motion itself? Or would we still be following the deeper rules of the cosmos? 76. The Grand Unified Theory. Gut. A force, a connection, a search for unity that has yet to be solved. Gravity is different. Electromagnetism, the strong force, and the weak force seem separate, but deep in the past, at unimaginable energies. They may have been one force. If we find the connection, we could explain the universe's structure itself. This is the Grand Unified Theory, GUT, not just a hypothesis, not just a mathematical trick, but a search for the hidden link between nature's forces. What is the Grand Unified Theory? The paradox asks, if forces were once unified, does that mean the universe has always been more connected than we see? If gravity remains separate, does that mean we are missing the deeper link? If gut is solved, does that mean we finally understand the true nature of reality? Different perspectives. Gut works. Because forces are similar at high energy. The electromagnetic force once merged with the weak force. At even higher energy, the strong force may merge too. So, what if? They were always one force? If we unify forces, can we manipulate reality? What if we controlled the fundamental interactions? What if we engineered force unification in a lab? Would we unlock new physics, or would we still be missing the deepest piece? If we never find gut, does that mean the universe was never unified? What if forces were never the same? What if nature has always been split? Would that mean we have been chasing a mirage? The truth about the Grand Unified Theory. The paradox challenges our understanding of forces versus unification, physics versus unknown connections, whether the universe is simpler than we think or more complex than we imagine. If forces were once unified, does that mean everything in the universe shares a single origin? 77. The search for supersymmetry, SUSY, a balance, a symmetry, a theory that predicts hidden particles that we have never seen. Every particle should have a superpartner. Electrons, quarks, and neutrinos should have twins. They are missing, undetected. But if we find them, we might solve dark matter. We might explain why particles have mass. This is the search for supersymmetry, SUSY. Not just an extension of physics, not just a guess, but a test for whether nature follows deeper patterns. What is supersymmetry, SUSY? The paradox asks, if every particle has a superpartner, why have we not seen them? If SUSY is real, does that mean physics has a deeper symmetry we have yet to understand? If SUSY is false, does that mean the standard model is the final answer? Different perspectives. SUSY works because symmetry has been the key to physics. Before electricity and magnetism were once thought separate, the weak force and electromagnetism were unified. So what if SUSY is the next big step? If we discover superparticles, does that mean we can understand dark matter? What if SUSY predicted dark matter's identity? What if we could confirm its existence? Would we solve one of the biggest cosmic mysteries? If supersymmetry fails, does that mean physics needs a new direction? What if we never find superpartners? What if nature is not symmetric after all? Would that mean we need an entirely new way to look at physics? The truth about supersymmetry, SUSY. The paradox challenges our understanding of symmetry versus discovery, predictions versus experimental reality, whether nature follows patterns or if physics is incomplete. If supersymmetry is real, does that mean the universe is built on hidden, unseen particles? 78. The cosmic microwave background radiation. A signal, a whisper, a faint glow from the birth of the universe. Look in any direction, and you see it. a uniform radiation left over from the Big Bang. It is cold, it is ancient, and it holds the secrets of the early cosmos. This is the cosmic microwave background radiation, not just a remnant, not just a discovery, but the oldest light we will ever see. What is the cosmic microwave background radiation? The paradox asks, if the Big Bang happened, does that mean its leftover heat should still exist? If the CMB is everywhere, does that mean we are looking at the past in real time? If the CMB has tiny variations, does that mean those fluctuations shaped the entire universe? Different perspectives. The CMB works because it confirms the Big Bang. A hot universe cooled down, photons were released, and they never stopped traveling. What if we are seeing the moment the universe became transparent? If we study the CMB, can we look further back in time? What if we decode its patterns? What if we understand its temperature changes? Would we learn about the first moments of existence? If the CMB did not exist, would that mean the Big Bang was wrong? What if the sky was empty of microwave radiation? What if the heat never cooled? Would that mean the universe was never born in a single explosion? 79. The fate of the universe. Big crunch, big rip, or heat death. A question, a prediction, a fate that depends on the hidden forces of the cosmos. Will the universe collapse back in a fiery end? Will it tear apart faster than light can catch up? Or will it fade into cold emptiness, never to change again? 3 possibilities, 3 endings, and no clear answer. This is the fate of the universe, not just theory, not just speculation, but a cosmic mystery waiting to be solved. What are the possible endings of the universe? The paradox asks, if the universe is expanding, does that mean it had a beginning and must have an end? If gravity fights expansion, does that mean the universe could collapse back into itself? If dark energy dominates, does that mean the universe will stretch apart until nothing remains? Different perspectives. The Big Crunch. Gravity wins. Galaxies slow down. Expansion stops. Everything collapses back into an ultimate singularity. A new Big Bang or the final end. The Big Rip. Dark energy destroys everything. The universe expands faster. Galaxies drift apart. Atoms split. Even space itself tears into nothingness. The heat death. A universe without motion. Stars burn out. Galaxies fade. Black holes evaporate until only cold emptiness remains. No structure, no heat, no life. The truth about the fate of the universe. The paradox challenges our understanding of cosmic expansion versus collapse, dark energy versus gravity, whether the universe has a cycle or an ultimate end. If the universe is heading toward its final fate, does that mean everything we do is just a temporary moment in an inevitable future? 80. Dark matter and dark energy, a force, a presence, a mystery that makes up 95% of the universe, but cannot be seen. Galaxies spin too fast. Light bends where nothing is visible. The universe expands, faster than it should. Something unseen is out there, something stronger than everything we know. This is dark matter and dark energy, not just missing mass, not just empty space, but the key to understanding the true structure of reality. What are dark matter and dark energy? The paradox asks, if we cannot see dark matter, how do we know it exists? If dark energy pushes the universe apart, does that mean it will never stop expanding? If most of the universe is dark, does that mean everything we see is just a small part of the whole picture? Different perspectives. Dark matter, the invisible mass holding galaxies together. We cannot see it. We cannot touch it. But without it, galaxies would fly apart. It is there, but we do not know what it is. Dark energy, the force that accelerates the universe. Gravity should slow expansion, but instead, the universe expands faster and faster. Why? because something is pushing it apart. If we solve dark matter and dark energy, do we unlock a new physics? What if they are not real things? What if our laws of physics are incomplete? Would solving them change everything we think we know? The truth about dark matter and dark energy. The paradox challenges our understanding of invisible forces versus known physics, expansion versus gravity, whether the universe is more than what we see, or if we are just missing the full picture. If 95% of the universe is dark, does that mean everything we understand is just a small piece of a much bigger puzzle? 81. The expanding universe and the Hubble constant, a movement, a measurement, a discovery that changed our place in the cosmos. Galaxies are moving away from us. The farther they are, the faster they move. Space itself is stretching. Distances grow. Light red shifts. This is the expanding universe and the Hubble constant. Not just an observation, not just a theory, but proof that the universe is not static, but alive. What is the expanding universe and the Hubble constant? The paradox asks, if the universe is expanding, does that mean it had a beginning? If expansion is accelerating, does that mean it will never stop? If galaxies move apart, does that mean the universe was once infinitely small? Different perspectives. The expanding universe works. Because space itself grows, galaxies are not moving through space. Space is expanding between them. And that changes everything. If the universe is expanding, what came before it? What if space was once infinitely small? What if time itself had a beginning? Would that mean there was a moment before the Big Bang? If expansion changes, could it reverse? What if the universe slowed down? What if it started contracting? Would we see a new big crunch? Or would space continue stretching forever? 82. The cosmic web and large-scale structure of the universe. A pattern, a network, a structure that spans the entire universe. Galaxies are not randomly placed. They form clusters, filaments, and voids. A cosmic web that stretches across billions of light years. Gravity pulls, dark matter shapes, expansion spreads, and suddenly, the universe looks less like chaos and more like a vast, interconnected structure. This is the cosmic web and large-scale structure of the universe, not just galaxies, not just empty space, but a grand cosmic design that reveals the invisible forces shaping everything. What is the cosmic web and large-scale structure of the universe? The paradox asks, if the universe is structured like a web, does that mean it follows hidden patterns? If dark matter holds galaxies together, does that mean most of the universe is made of something we cannot see? Space, does that mean their fates are linked? Different perspectives. The cosmic web exists because gravity shapes everything galaxies form along filaments. Mass clumps together over time, and suddenly, the universe looks like a living structure. If galaxies follow a pattern, could we predict the future of the universe? What if we mapped the entire web? What if we understood how filaments evolve? Would that mean we could see the fate of the cosmos? If we could see the full cosmic web, would we see the universe differently? What if our galaxy was just one node in a vast network? What if every star was part of a larger design? Would that mean we are not as isolated as we think? 83. The anthropic principle and fine-tuning. A question, a mystery, a universe that seems perfectly suited for life. The constants of physics are precisely tuned. Too much gravity, no stars, too little nuclear force, no atoms, too fast an expansion, no galaxies, and yet everything is just right. Is it coincidence, or is the universe designed for observers like us? This is the anthropic principle and fine-tuning. Not just luck, not just numbers, but a deep question about why the universe is the way it is. What is the anthropic principle and fine-tuning? The paradox asks, if the universe is fine-tuned for life, does that mean it was designed? If small changes to physics would make life impossible, does that mean our existence is incredibly rare? If there are infinite universes, does that mean fine-tuning is just selection bias? Different perspectives. The anthropic principle works because life can only exist in certain conditions. If the cosmos was different, we would not be here to ask the question. We exist because conditions allowed it. But does that mean anything deeper? If the universe is designed for life, who or what set the rules? What if these laws are intentional? What if the numbers were chosen? Would that mean the universe has a purpose? If there are infinite universes, does that explain the fine-tuning? What if our universe is just one of many? What if every possibility exists somewhere? Would that mean fine-tuning is just statistical inevitability? Or would we still search for a higher explanation? 84. The black hole information paradox. A collapse, a singularity, a problem that breaks physics itself. A star falls into a black hole. Its mass remains, its gravity stays, but its information disappears. Quantum mechanics says information cannot be lost. General relativity says it is gone forever. Both cannot be true. And yet, no one knows the answer. This is the black hole information paradox. Not just a puzzle, not just a contradiction, but a clash between two of the most powerful theories in physics. What is the black hole information paradox? The paradox asks, if information is lost in a black hole, does that mean physics is incomplete? If quantum mechanics is right, where does the information go? If general relativity is correct, does that mean black holes erase the past? Different perspectives. The black hole information paradox exists because two theories conflict. Quantum physics says information is never lost. Relativity says black holes destroy it. And yet, both theories work everywhere else. So which one breaks down? If black holes destroy information, does that mean the universe can forget? What if information is truly erased? What if the past can be lost forever? Would that mean physics is not as reversible as we thought? If information is hidden, could we ever retrieve it? What if information escapes in some unknown way? What if black holes do not erase but encode? Would that mean there is a way to unlock the secrets inside? Or would we still be left with a fundamental mystery? 85. The role of neutrinos in cosmology. A particle, a mystery, a ghost-like presence that shapes the universe. Neutrinos pass through Earth, through you, through everything. Trillions of them flow every second, without interacting. But they were there at the Big Bang. They influence galaxies, stars, and cosmic evolution. This is the role of neutrinos in cosmology. Not just a subatomic particle, not just a weak interaction, but a key to understanding the early universe. What is the role of neutrinos in cosmology? The paradox asks, if neutrinos barely interact, does that mean they are invisible to the forces that shape the universe? If neutrinos were created in the Big Bang, does that mean they hold clues to the birth of everything? If neutrinos have mass, does that mean they could help explain dark matter? Different perspectives. Neutrinos are cosmic messengers from the earliest moments of the universe. A supernova explodes. Neutrinos arrive first. A black hole forms. Neutrinos carry the news because they pass through everything. If neutrinos have mass, could they solve the dark matter puzzle? What if neutrinos outnumber all other particles? What if their mass is enough to influence galaxies? Would that mean they are the missing mass of the universe? If we could control neutrinos, could we unlock new physics? What if we harnessed their properties? What if we built neutrino detectors across the cosmos? Would we see hidden forces at work? Or would we still struggle to detect these ghost particles? 86. The origins of the universe and the inflation model. A beginning, a burst, a moment when the universe expanded faster than light. Space itself inflated. Quantum fluctuations stretched across the cosmos. Galaxies were seeds in a quantum storm. And in less than a trillionth of a second, the universe became what we see today. This is the inflation model. Not just the Big Bang, not just expansion, but the deepest mystery of cosmic origins. What is the inflation model? The paradox asks, if the universe inflated faster than light, does that mean space itself has no speed limit? If inflation happened in a fraction of a second, does that mean the entire universe was once smaller than an atom? If quantum fluctuations seeded galaxies, does that mean randomness shaped everything we see? Different perspectives. The inflation model explains the large-scale structure of the universe. A tiny quantum ripple, a massive galaxy, because randomness in the beginning became the structure of everything. If inflation happened, does that mean the universe had no real beginning? What if the Big Bang was just one event? What if inflation happened before time itself began? Would that mean the universe has always existed? If we could recreate inflation, could we create new universes? What if we triggered rapid expansion? What if we controlled space itself? Would we build new cosmoses? Or would we still be unable to touch the origins of everything? The truth about the origins of the universe and the inflation model. The paradox challenges our understanding of space versus time, quantum fluctuations versus large-scale structure, whether inflation was a single event or something that happens eternally. If inflation created the universe in a fraction of a second, does that mean we are all living in the aftershock of a quantum storm? 87. The second law of thermodynamics and the arrow of time. A direction, an increase, a rule that says the universe never goes backward. Heat spreads, order dissolves, stars burn, entropy always increases. The past is structured, the future is chaos, and that is why time only moves forward. This is the second law of thermodynamics and the arrow of time. Not just physics, not just disorder, but the reason why yesterday is gone forever. What is the arrow of time? The paradox asks, if entropy always increases, does that mean time only moves in one direction? If the universe started in low entropy, does that mean the past was more ordered than the future? If everything moves toward equilibrium, does that mean time itself will eventually stop? Different perspectives. The arrow of time works because entropy defines the flow of events. A broken egg does not reassemble. A shattered glass does not restore itself because entropy never decreases. If time is linked to entropy, could we ever reverse it? What if we could reduce entropy? What if we could extract energy from disorder? Would we turn back time? If the universe reaches maximum entropy, does time cease to exist? What if the universe runs out of useful energy? What if entropy reaches its peak? Would time freeze, or would something new emerge from the chaos? 88. The Planck scale and quantum gravity. A limit, a boundary, a scale so small that space itself may break apart. At the Planck length, distance loses meaning. At the Planck time, past and future blur. Gravity and quantum mechanics collide, and physics as we know it stops working. This is the Planck scale and quantum gravity. Not just small numbers, not just a theoretical idea, but the deepest mystery in physics, where space, time, and gravity meet in ways we do not yet understand. What is the Planck scale and quantum gravity? The paradox asks, if space-time stops behaving normally at the Planck scale, does that mean space is made of something deeper? If time loses meaning at the smallest scales, does that mean time itself is just an illusion? If gravity and quantum mechanics conflict at the Planck scale, does that mean physics is incomplete? Different perspectives. The Planck scale works because it defines the smallest possible units of reality. A meter is big. A millimeter is smaller. A nanometer is microscopic. But the Planck length, it is the limit, the smallest meaningful distance. If space-time becomes chaotic at the Planck scale, What lies beyond it? What if space is not continuous? What if time is not smooth? Would that mean reality is built on something even smaller? If we understand the Planck scale, do we unlock the secrets of the universe? What if we found a true theory of quantum gravity? What if we combined relativity and quantum mechanics perfectly? Would we finally see the hidden structure of reality itself? The truth about the Planck scale and quantum gravity. The paradox challenges our understanding of small versus smallest space versus quantum chaos, whether reality is continuous or pixelated at the deepest level. If space and time break down at the Planck scale, does that mean reality is built from something even more fundamental? 89. The possibility of white holes. A collapse, a singularity, a black hole, but in reverse. Black holes pull everything in. White holes push everything out. No one has ever seen one. No one knows if they exist. But if they do, they may be the other side of black holes, or even gateways to another universe. This is the possibility of white holes, not just a wild idea, not just science fiction, but a theoretical counterpart to the most mysterious objects in the cosmos. What are white holes? The paradox asks, if black holes consume matter, does that mean white holes must eject it? If nothing can enter a white hole, does that mean it is the opposite of a black hole? If white holes exist, could they explain the unexplored parts of the universe? Different perspectives. White holes could exist as the reverse of black holes. A black hole traps light. A white hole expels light. One pulls space inward, the other pushes it outward. And suddenly, the universe feels balanced. If white holes exist, where do they lead? What if black holes connect to white holes? What if matter falls into one and exits the other? Would that mean they are portals to another reality? If we find a white hole, could we harness its energy? What if white holes spit out energy? What if they produce new matter? Would that mean they are the engines of cosmic creation, or would they still be beyond our reach? 90. The simulation hypothesis in physics. A question, a possibility, a theory that turns reality upside down. What if the universe is not real? What if it is a simulation? What if the laws of physics are just rules in a programmed system? A computer, a creator, a reality that may be nothing more than code running on an unimaginable machine. This is the simulation hypothesis in physics, not just a philosophical question, not just science fiction, but a possibility that modern physics may already be pointing toward. What is the simulation hypothesis in physics? The paradox asks, if the universe follows strict mathematical laws, does that mean it was designed? If space and time have limits, does that mean they are just part of a simulation's resolution? If we live in a simulation, could we ever prove it? Different perspectives. The simulation hypothesis works because the universe looks like a computer program. Reality has rules. Physics has limits, and like any simulation, there may be a hidden structure running in the background. If we are in a simulation, who or what created it? What if an advanced civilization built it? What if we are just characters in their program? Would that mean they could shut it down at any time? If we discover the truth, could we hack the simulation? What if we found the source code? What if we modified the laws of physics? Would we become gods within the system? Or would we still be prisoners of the simulation's design? 91. The omega point theory. A future, a singularity, a universe racing toward infinite intelligence. Everything evolves, minds merge, knowledge expands, and at the end of time, the universe reaches the omega point, a state of infinite complexity, a moment where all consciousness unites, and time itself transcends. This is the omega point theory, not just speculation, not just philosophy, but a bold cosmological hypothesis. That suggests the universe is evolving towards something beyond comprehension. What is the omega point theory? The paradox asks, if intelligence grows forever, does that mean the universe is designed to think? If knowledge has no limit, does that mean time itself will never end? If consciousness can shape reality, does that mean the final state of the universe is just pure thought? Different perspectives, the omega point works, because complexity increases over time. Simple atoms formed molecules. Molecules formed life. Life evolved into intelligence. And intelligence may evolve into something even greater. If the universe is moving toward infinite thought, are we part of a cosmic mind? What if we are just early versions of something far more advanced? What if we are evolving toward a universal mind? Would that mean we are the first sparks of something infinite? If the omega point exists, what happens when it is reached? What if all knowledge is gathered? What if all intelligence is merged? Would time cease? Would existence transcend? Or would we still be searching for meaning in a universe that has already found it? 92. The Beaconstein, bound and limits of information storage. A number, a limit, a fundamental restriction on knowledge. Every object holds information. Every particle contains bits of data, but there is a maximum amount. That can fit inside any space. No infinite memory, no endless knowledge, just a hard limit on how much the universe can store. This is the Beaconstein bound, not just physics, not just computation, but a fundamental limit on reality itself. What is the Beaconstein bound? The paradox asks, if the universe has a maximum information capacity, does that mean knowledge is finite? If black holes store information at their surface, does that mean reality is a hologram? If no system can hold infinite data, does that mean there is a limit to how much can ever be known? Different perspectives. The Beaconstein bound works. Because information is linked to energy, more mass, more energy, more possible states. But there is a limit. Beyond a certain point, information cannot increase. If information storage has a limit, does that mean reality is a simulation? What if space itself is a computing system? What if the universe is processing data? Would that mean reality is just a cosmic information processor? If we reach the information limit, what happens next? What if we fill the universe with knowledge? What if no new data can be stored? Would we stop discovering? Or would we find that some knowledge cannot be recorded? 93. The role of quantum decoherence. A choice, a collapse, a world of possibilities that suddenly disappears. A quantum system is in superposition. It holds many states at once. But then, it interacts with the environment. The possibilities vanish. Only one outcome remains. This is quantum decoherence. Not measurement, not observation. Just the moment quantum states become classical reality. What is quantum decoherence? The paradox asks, if a quantum system loses coherence, does that mean the universe constantly destroys possibilities? If observation is not required for wave function collapse, does that mean reality does not need an observer? If decoherence is just an interaction with the environment, does that mean quantum effects are all around us but invisible? Different perspectives. Quantum decoherence works. Because systems are always interacting. A particle exists in many states, but the moment it touches the environment, it picks just one, and suddenly, superposition vanishes. If decoherence is what creates classical reality, does that mean measurement is not special? What if an observer is not required? What if a quantum state collapses, simply because it interacts with a dust particle? Would that mean quantum mechanics does not care about us at all? If we could control decoherence, could we control reality? What if we stopped interactions? What if we preserved superposition forever? Would we create a world where multiple realities coexist? Or would we still be bound by the single path of time? 94. Quantum gravity and the fabric of space-time. a force, a quantum field, a theory that does not yet exist. Gravity warps space-time. Quantum mechanics governs the tiny, but together, they do not agree. Black holes defy predictions. The early universe breaks equations. Because something is missing. This is quantum gravity and the fabric of space-time. Not just a problem, not just a theory, but the key to unifying physics. What is quantum gravity and the fabric of space-time? The paradox asks, if space-time is curved by gravity, does that mean it is made of something? If quantum mechanics and gravity conflict, does that mean one of them is incomplete? If quantum gravity exists, does that mean space itself could be quantized? Different perspectives. Quantum gravity works because it seeks to connect the very large and the very small. A black hole singularity should not exist. The Big Bang equations should not break down, because somewhere, quantum mechanics and relativity must merge. If space-time has a quantum structure, what is it made of? What if space was not continuous? What if time came in tiny units? Would that mean reality is just a collection of quantum bits? If we discover quantum gravity, do we unlock the final theory of physics? What if we found the missing link? What if gravity was just another quantum force? Would we explain everything? Or would we still find new mysteries hiding in the equations? 95. The relationship between quantum mechanics and general relativity. A contradiction, a paradox, a battle between two great theories. Quantum mechanics explains the small. General relativity explains the large. Both are tested, both are correct, but together, they break down. Black holes lose information. The early universe defies prediction, and physics itself seems incomplete. This is the relationship between quantum mechanics and general relativity. Not just a conflict, not just an equation, but a problem that must be solved. What is the relationship between quantum mechanics and general relativity? The paradox asks, if relativity and quantum mechanics both work, does that mean one of them is still missing something? If space-time curves, but particles exist in quantum states, does that mean gravity has a quantum nature? If physics must be unified, does that mean we are still missing the fundamental law of the universe? Different perspectives. General relativity and quantum mechanics work separately but not together. A star collapses. General relativity works. A particle behaves like a wave. Quantum mechanics works. But put them in the same equation, and the math breaks down. If general relativity is classical, does that mean it is incomplete? What if gravity is not really a force? What if it is emergent from quantum interactions? Would that mean we need a new theory of space-time itself? If we unify quantum mechanics and relativity, do we solve every mystery? What if we found the final equation? What if we explained black holes, the Big Bang, and dark matter? Would that mean physics is finally complete? Or would the universe still keep its deepest secrets hidden? 96. The emergent nature of space-time. A fabric, a reality, a question that challenges everything we know. Is space-time fundamental, or does it emerge from something deeper? Quantum entanglement suggests information. Holography suggests space is an illusion. Gravity suggests connections between points. And suddenly, space itself feels like a construct. This is the emergent nature of space-time. Not just a theory, not just an idea, but a shift in how we see reality itself. What is the emergent nature of space-time? The paradox asks, if space-time is not fundamental, does that mean it is just a useful illusion? If quantum entanglement builds space, does that mean connections define reality? If space-time emerges from information, does that mean the universe is just a processing system? Different perspectives. Space-time might be an emergent property of deeper quantum laws. A black hole encodes information. A quantum state is non-local. And suddenly, space is not where things happen. It is what information creates. If space is emergent, What exists beyond it? What if space itself is built from quantum states? What if time is just a result of entanglement? Would that mean there is a deeper reality outside our own dimensions? If space is not fundamental, does that mean the universe is just a simulation? What if reality is not continuous? What if everything is just data and connections? Would that mean the universe is a computational process? Or is there still something deeper we have yet to see? 97. The search for a unified theory of physics, a force, a connection, a quest to combine all of physics into one theory. Newton unified motion and gravity. Maxwell unified electricity and magnetism. Einstein connected space, time, and gravity. But quantum mechanics and relativity still don't fit together. Two great theories, two different realities. One must be incomplete. This is the search for a unified theory of physics, not just a dream, not just a hypothesis, but the ultimate goal of science. To explain everything with one equation. What is the search for a unified theory of physics? The paradox asks, if physics is universal, does that mean there must be a single theory that explains everything? If quantum mechanics and relativity contradict each other, does that mean one of them is wrong? If a unified theory exists, does that mean the universe is just a mathematical structure? Different perspectives. A unified theory works because it brings together all fundamental forces. Electromagnetism, the weak force, the strong force, gravity. If they all come from one fundamental principle, then physics would finally be complete. If a unified theory exists, does that mean everything is determined by mathematics? What if the universe is just numbers? What if reality is just equations? Would that mean everything we experience is already encoded in a single formula? If we find the theory of everything, what comes next? What if we solve the final puzzle? What if physics is fully understood? Would that mean there is nothing left to discover? Or would we still find new mysteries beyond the equation? 98. The cosmic censorship hypothesis. A collapse, a singularity, a place where the laws of physics break down. A black hole forms, space and time crumble inside it. But what happens at its center? No one knows, because nature hides singularities behind event horizons. We can never see them, we can never study them, because reality censors its deepest secrets. This is the cosmic censorship hypothesis, not a law, not a proof, but a question about whether nature protects us from its own contradictions. What is the cosmic censorship hypothesis? The paradox asks, if singularities exist, does that mean the universe hides them for a reason? If the laws of physics break inside a black hole, does that mean physics itself is incomplete? If singularities were visible, would we see things that defy all logic? Different perspectives. The cosmic censorship hypothesis works because no naked singularities have been observed. Every black hole has an event horizon. Every singularity is hidden from view. And that is why physics still makes sense. If we could see a singularity, would we witness the breakdown of reality? What if a singularity was exposed? What if we could study it directly? Would we see infinite density? Or would we discover that singularities don't exist at all? If cosmic censorship is true, is the universe protecting its own secrets? What if nature erases paradoxes? What if reality prevents contradictions? Would that mean some answers were never meant to be known? 99. The role of entropy in the evolution of the universe. A disorder, a change, a law that says everything moves toward chaos. Stars form, galaxies collide, black holes evaporate, and in the end, entropy always increases. The universe was once ordered. It is now expanding, cooling, unraveling. One day, there will be nothing left. This is the role of entropy in the evolution of the universe. Not just about heat, not just about randomness, but a cosmic fate that may be unavoidable. What is the role of entropy in the evolution of the universe? The paradox asks, if entropy always increases, does that mean the universe is doomed to heat death? If disorder grows over time, does that mean everything is just a temporary structure? If entropy defines the future, does that mean time itself only flows forward? Different perspectives. Entropy works because it describes the direction of time. A broken glass never reassembles. A star never unburns. A universe never reverses its expansion because entropy always moves forward. If entropy always wins, does that mean the universe will end in silence? What if all energy is evenly spread? What if all processes stop? Would that mean the universe reaches a final motionless state? If we understand entropy, can we reverse it? What if we learned to reduce disorder? What if we discovered a way to rebuild structure? Would we fight the fate of the universe? Or would we still be bound by the arrow of time? 100. The quest for a theory of everything. A question, a search, a single equation. That explains everything. Quantum mechanics rules the small. General relativity rules the large, but they do not fit together. Gravity fights with quantum theory. Space-time bends, but particles behave unpredictably. And physicists seek the bridge. That will unite them all. This is the quest for a theory of everything. Not just another theory, not just another formula, but the final key to understanding the entire universe. What is the theory of everything? The paradox asks, if we find a single theory that explains everything, does that mean physics is complete? If quantum mechanics and gravity do not fit together, does that mean one of them is wrong? If we discover the final equation, does that mean we will finally understand reality itself? Different perspectives. A theory of everything would unify all fundamental forces: gravity, electromagnetism, the weak force, the strong force. If they are all part of one system, then everything is just different expressions of the same fundamental reality. If we find the ultimate theory, would it answer every question? What if we discovered the final equation? Would we know why the universe exists? Would we know what came before time? Or would we still find deeper mysteries hidden beneath the surface? If reality can be explained in one equation, what does that say about us? What if we are just part of the math? What if free will, thought, and existence are just patterns in an equation we cannot yet see? Would that mean the universe is just a mathematical structure? Or would we still believe that some things exist beyond physics? The truth about the quest for a theory of everything. The paradox challenges our understanding of unification versus fragmentation, final answers versus infinite questions, whether the universe is truly explainable, or if some things will always remain beyond understanding. If a single theory explains everything, does that mean we have reached the end of physics, or just the beginning of something deeper?